Today we have the pleasure to have with us Carleton Coffrin. Carleton is a staff scientist at Los Alamos National Lab. He got his PhD from Brown University in the US, and then he moved to Australia for a couple of years, and came back. Carleton is actually quite active today. He's going to talk to us about quantum computing and the power models in Julia. He has received the Los Alamos National Lab Early Career Award. He has received an award for leadership in quantum computing. He has received an award for distinguished performance. And also he's an editor for the Informs Journal on Computing. And without further ado, Carleton, the floor is yours.
Great. So thank you, everybody, for coming to this summer school and my lecture in it. And thank you to the organizers for inviting me to come and speak. When Spiros first reached out to me, he said, would you talk about quantum computing? And I was like, OK, sure, quantum computers are really fun and cool. But I'll come if I can also talk about power models and optimal power flow. So I had a tough decision to make earlier this week. Which one would I talk about first? We have all morning, right? And I decided that I would start with the optimal power flow in Julia because I think there's a very high probability what we talk about in this lecture could impact your research today. I love Julia. I love optimization. And the tools we're building in Julia are extremely useful. So that I'll begin with this piece. Now, the quantum computing piece will be the second part of the talk, and that would I expect it'll be about 2/3 of the time this morning. And that is much more speculative. So I'm going to focus on kind of teaching you the basics of quantum computing so you can go and read a paper and understand what it's about. But I think the potential use cases of it are much more they're not well understood, and it's kind of hard to make a case a lot of the time. We'll talk a bit about it, but I think the probability that quantum computing changes your research tomorrow is lower, but it's really fun and interesting. So that's why I decided to go with optimal power flow first. For the whole, so we have 3 hours. That's a lot of time. I'm planning to take a short break, maybe each hour-ish, so that I can refill my water, and everyone else can just clear your head for a moment. But throughout this whole morning, please interrupt, please ask questions, right? I am here to teach you, and the best way to do that is to just ask me when something's not clear or you just want to know more about something. I'm here for you. So, any initial questions? All right. So let's get into it. AC optimal power flow in Julia. I have 3 key messages I want you to take away from this talk. The first one is that Julia, which is a newish programming languages, and Jump, which is the optimization modeling layer in Julia, are really great tools for R&D and energy systems. Second thing is that I helped build at Los Alamos this tool called PowerModels, and that may be useful to you too. That's our transmission level modeling software, and it's got lots of really cool tools for power network optimization in it. And last but not least, I love AC optimal power flow, and maybe you should too because it's super cool. All right. So here's an overview of the parts of this talk, and like I said, this is maybe 45 minutes to an hour long worth of content. So I'm going to begin by telling you about critical infrastructure modeling at LANL. That's the software tools that we've been building over the past couple of years. I'll give you a very brief introduction to AC optimal power flow because I just want us to all be on the same page with the notations that I'll be using. I presume most of the people in the room know the foundations of AC optimal power flow. Then I'll talk a bit about how you can model that AC optimal power flow in Julia and Jump. And last, or maybe the most interesting part of this section, is talking about where all the time goes, computational time, when you're solving an AC power flow problem, and how you can potentially improve it. We've done a fair bit of research in the last couple of years to make AC optimal power flow faster in Julia. So that's the outline. Critical infrastructure modeling at LANL. So This started back in 2016. We sought to build some open source critical infrastructure modeling tools. It began with PowerModels, and that was just kind of a passion project of mine. I had been doing power flow relaxations research when I was in Australia, as Spiros mentioned, in the previous years. And when I got to LANL, everyone was like, we love Julia, we should all be using Julia. And so I was like, well, let's see if we can do transmission network modeling in Julia and get it to be state of the art in terms of performance and sophistication. And that worked out really well. I was pleasantly surprised that the modeling layer that we were using, which is called JUMP, was able to scale to real size networks and worked as well as any other tool I'd ever used. So that kind of became the beginning of this transmission network modeling capability, and then what has grown over the last years into a broader infrastructure modeling capability. So now, by 2021, so that was 5 years after I started, but still a couple years ago, we've grown the ecosystem of infrastructure modeling tools beyond just power transmission. So now we have power models distribution for multi-phase distribution modeling. We've got gas models, which is for natural gas transmission modeling. Water models is for potable water distribution modeling. And then petroleum models is it's maybe our least well-developed framework, but it is for petroleum transmission modeling, so liquid in pipes. These are definitely, I could not do all of this alone, so there's a variety of other scientists at Los Alamos who support different aspects of these projects. And there's even more people now that I don't have listed on these slides, but these were kind of the people who built the first versions of many of these packages. Overall, this collection of infrastructure modeling is about 85,000 lines of code. It represents thousands of labor hours across all of these staff scientists, so it's a really big investment in time. And I mean, from a software perspective, 85,000 lines of code is not a lot, but at the level that we're talking about, like Julia, mathematical programming, that's actually like quite a significant amount of software. So for the rest of this talk, I'm only going to focus on power models because that's the transmission modeling one. I think it's the most relevant to what we're talking about here. But you should definitely check out all of the different packages if any one of them is interesting to you. The common theme of these infrastructure modeling packages is the following. So for every single one of them, we try to take inspiration from things that have worked really well in the research community and then do it over and over again in different sectors. So we have, each one of these tools has a modeling layer, which is kind of like a mathematical programming modeling layer, but specialized for infrastructure systems. And I'll show you an example of that later in this talk. Then we have a minimalist data format. So you may be familiar, like when you load a power network data set, it like comes in either a MATLAB, like MATPower format, PSSE. If you're doing distribution modeling, you've got like GridLabD, OpenDSS, SIME. There's like all these formats. Most of the industry formats are really difficult to use. I don't know if you've ever tried to parse one of those. It's like really crazy. But one of the successes that MATPower had was that they defined a network data format that was really easy to use. You can just look at it in a table form and like understand what's going on. So first, we support these standard data formats, but we also always make sure that we have an academic one like MATPower, or we developed one for gas networks called MATGAS because it really makes a big difference if you have a data file that's easy to understand. All of the packages are made with similar software standards, so if you can learn how to use one of them, you'll find that there's like a very similar design and data structure for each of the other ones, so that way you can kind of transfer your knowledge from one package to the other. So the goal is that it's really easy to learn all the different packages once you've learned one of them. And then we actually do a lot of work to make sure that they integrate with each other. So if you want to do multi-infrastructure modeling, couple a power network to a gas network, or a water network to a power network, these types of things are very easy to do in our system. I also have pglib up on the slide. You may be familiar, so there's a collection of AC optimal power flow cases, which I've helped to maintain for the last decade, called the Power Grid Library for Optimal Power Flow. That's going to come up in the future. in this talk, so I just mentioned it here. But that's another aspect of the work we're doing at LANL. We try to build these standard benchmark libraries so that we can maintain our software, track its performance, but also give them to the community to do good research on. So let me just show you an example of what it looks like to do a simple optimal power flow study in PowerModels. So now we're just in transmission modeling. If you're used to map power or something similar, that is what we're going to show you here. So this is Julia syntax. The close bracket when you're in the Julia REPL means I want to enter the package manager. So I'm going to enter the package manager, and I'm going to add PowerModels for doing that transmission network modeling. And then I'm going to add a package called IPOpt. IPOpt is an interior point solver, which allows you to solve convex, continuous convex problems or continuous non-convex problems. It's an incredible tool, especially for power network modeling. So that's the default we picked. There's many other solvers you could use, but that's the one that I'll use in this talk. So this will install on your computer all the key packages you need for doing the analysis. The next step is that you need to load some data. So after you're done installing the package, you then can start loading it into your environment and using it. So the command using in Julia is how you pull a package into your current working environment. That will load some standard functions, like in this case, parse file is a function that's defined by PowerModels for reading transmission network data sets. So if I do parse file and then I give it a path to a data set on your computer, it will try to load it. If in this case I'm loading the pglib OPF case 5, that's one of the smallest cases, as 5 buses. It's inspired by some ancient PJM system. PJM is one of the power network operators in the US. And you run parse file, you'll most likely see a bunch of messages in the terminal. As it reads the data, it provides it some information. And then you get this network data structure that you can work with. The first thing, and the most useful thing, I think, to do with the network data is to call this function called print summary, which tries to give you an overview of what's going on in the data. Now you have the data in your Julia session. You can start to try to solve an optimal power flow problem or something similar. So now if we want to solve a problem, we need a mathematical tool for solving it. That's why we need IPOpt. So using IPOpt is what brings in the IPOpt library. And now PowerModels defines functions like solve AC OPF, solve DC OPF. And those solve methods require the network data, which we loaded in the previous step, and the solver that you want to use to solve it. So in this case, we're going to use IPOpt, and the syntax is that you just say .optimizer after the package name to get the solver. When you're done, the print summary function, which works on the network data, it also works on the results data. So you get some results back. It includes things like the status of the solver, what the objective function was. But most often, you're going to want to look at the solution data. So that's the information about what the power flow was that was found by the solver. And you can use print summary to print that solution data. And I suspect it's pretty self-explanatory. If you do solve AC, you're going to solve a nonlinear problem with all of the voltage and reactive power and active power. When you do solve DC OPF, you're going to solve it with just the active power only approximation with a linear power flow solver. Any questions so far? Okay. So I wanted to show you a little bit of what the network data looks like, because it will come up in later slides. So when you parse, what you see at the bottom of this slide is what a map power for a transmission network data set looks like. So you've got essentially a bunch of matrices. There's a matrix for the buses in the network, where every column is a specific data field. And then when you go to the branches, you again have a matrix, and then each column is a different data field. Each row is either one of the buses or one of the branches. So that's what it looks like inside of the .m file or the map power file. When you load this into PowerModels or one of the other LANL packages, we actually don't use a table format. We use what's called a dictionary. So it can be like a nested data structure. So what you're going to see is something that's more like just the top level keys of all of the different components. So there'll be a dictionary of buses, a dictionary of branches, and essentially you index into this dictionary to extract key information. So here's 2 examples. If you do network data, then you want to look at the buses, then you give a bus identifier, so that would be 1 in the example here. Now I want to look up, say, the voltage magnitude at that bus. VM is the keyword for the voltage magnitude. And so if you execute that first line, you'll get 1 because it looks up that particular value in that table. To give you a more interesting example, if you're looking at branches, so these are the lines in the network, you would say, okay, I want to look at the branches. I want to look at branch number 3. I want to know the reactance on that branch, which is BR_X, and it would give me 0.0064. So that's the data. That's how the data gets loaded inside of Julia. I mentioned this mathematical programming modeling layer. So at the highest level in the modeling system of PowerModels and the others, you actually have a function that looks like this. So it'll say like build OPF. It doesn't say AC, it doesn't say DC, it doesn't specify any of those details, but it has a standard section where you declare the variables that you want in your problem, then you'll define your objective function, and then you start building up your constraints. So these are the decision variables. You can see they're like all variable underscore. You have your objective function, and then this is the block of constraints. Now, the important reason why I'm showing you this is that there's a lot of structure in this particular mathematical program or optimization problem that's really specialized to power networks, right? So we're looping over all the reference buses, and we're saying like we want to make the reference bus constraint. Whereas for every bus, we want a power balance constraint. For every branch, we need to implement the Ohm's law. We need to implement difference, like the flow constraints, either angle difference or thermal limits. And this is kind of the canonical OPF formulation, but there's many variants you can find in power models with like current constraints or other pieces. And essentially, you like remove some section of this block and replace it with other ones with different names, and you get the kind of infrastructure level modeling that you're interested in. The thing that was my main inspiration for building this, it really comes down to this function. So you have build OPF, and it's defined over a thing called a generic power model. If you want to build a DC approximation of this particular optimization, or you want to do the full AC, or you want to do the AC in different coordinate spaces, or you want to do a convex relaxation, they will all use this same function. So the definition of the problem, of what the OPF problem is consistent in all cases. But the interesting thing here is that what gets executed in each of these functions will change based on if you're asking for those different versions of the power flow problem. But the underlying goal remains the same. So that was my main inspiration for this. And this is one of the reasons why power models and our other tools are really good if you want to try lots of different formulations, like AC, DC, convex relaxations, there's tons of them. This is what it's good for. Okay, so that is kind of the broad introduction to what the infrastructure modeling tools are. I wanted to briefly mention some lesser known features that I think are really useful. The first one I'll mention is that there is, in addition to all this jump modeling layer optimization, we actually built an AC power flow solver from scratch. So if you want to see what a pure Julia Newton method type of AC solver is, you can check out this particular part in power models. So that's about as fast as of an AC power flow that I know of. We also have a feature called basic network data. If you are working with real industry data sets, you have to support a very complicated model of a transmission network. But it's kind of difficult to do a standard textbook example when you have such a complicated network model. This basic network data gives you an easier way to, like, it simplifies the network so that you can then do a textbook exercise with the data that you have in Power Models. There's lots of PowerFlow approximations and relaxations. I mentioned some of these before. We have DC with line losses, approximation called LPAC that we developed some years ago, and then tons of convex relaxations. So if you want to study convex relaxations, you'll get pretty much a very solid baseline of methods out of the box with Power Models. There is a very nice tool for optimization-based bound tightening, which is an advanced technique for deducing what values different variables in your OPF problems can take. And last but not least, there is an extremely scalable DC second-order security-constrained OPF implementation. So if you want to solve that problem really scalably, you need to be very clever about modeling the contingency stages and then adding cuts into the master problem. The last time I checked it, which was several years ago, this particular implementation could run DC security-constrained OPF on a 30,000 bus network with 10,000 contingencies in about 2 hours on a laptop like the one I'm presenting from. So that is pretty fantastic. It took me many years to get to that level. One of the greatest achievements for Power Models that I am happy about is that we have engaged in this ARPA-E grid optimization competition where ARPA-E was giving millions of dollars away for people who could solve really challenging grid optimization problems. And tools based on Power Models consistently ranked in the top performers of this competition, like top 10 or top 5. And to me, that meant that even though this tool is in Julia, even though it's really designed for research purposes, you can get state-of-the-art performance out of it, and it could be like ready for industry scale problems running at industry speeds. So don't be shy. If you learn Power Models in Julia, you can then take it into real-world applications. That's the end of the Power Models part. And the next part, I'll just start talking about optimal power flow. Any questions? We got one back there.
So, in regards to like different solvers, what kind of different solvers work with Power Models? Like, for instance, can you also use Gurobi solver, IOP, Jump? Is there like a performance difference between using these different solvers?
Yeah, so just repeating the question. The question is what solvers are supported in Power Models. Power Models is built on Jump. So every solver that's supported by Jump is supported by Power Models. You mentioned Gurobi. Highs is another popular open source one. If you're looking at nonlinear, we have IPOPT is the free one. Nitro is the commercial one. Yeah, you can try all of these things. And it's fun to test them. Was there another question? Okay. Yeah, solvers are great. And that's one of the reasons why we at LAML built all these infrastructure modeling tools on Jump. That gives us an abstraction layer where we're not dedicated to a specific methodology, right? It makes it easy to switch. Okay, so introduction to AC optimal power flow. This is going to be very brief because I'm presuming most of you know the basics. So what is AC optimal power flow? The way I think about this, because I come from a computer science background and not power systems, and optimization, the operations research background, I think of power network, AC optimal power flow as like the canonical nonlinear optimization, like network optimization problem. So we're just trying to, we have some fixed demands in a transmission network, and we're trying to set the generators to get a minimum cost generation profile. But we also have some basic operating constraints, like how much flow can go across each edge in the network, what is the limits on the voltages. And then, of course, the most interesting one is this Ohm's law constraint, which defines how power flows through a network, right? We have a number of buses, and then at least, from my perspective, the way I think about it these days is that if you have less than 500 buses in your network, are kind of like a toy problem. That's, maybe good for some analytical work. Once you're in the 500 to 5,000 range, you're really in like R&D. You won't have reviewers complaining of your papers if you get top 5,000 buses. They'll be pretty impressed. But if you really want to go to industry scale, you need to get up to like 50,000 buses. That's the scale that many industry entities would really like to be solving. So this is the way I'm going to write AC optimal power flow, like in the most general form. So I'm calling this the complex form. So in this version, each of the decision variables is a complex number, and I'm not actually like projecting it into real numbers yet. So there's no implied way of like how you would implement this. It's just like, well, we have some generators and they exist in a complex plane with upper and lower bounds. That's like the box of real and reactive power. That's what the first one is saying. The second one is saying like, yeah, you have line flows, which are complex valued as well, and they're within some box, which has to do with the total maximum flow on the line. And then the next one is the voltages, which have a bounds on the voltage magnitude, but no particular bound on the angle. In this form, when you define the objective function, remember that the cost of power generation is usually just defined on active power. So you need to take the real component of the generation variable and then put it through a function. Here, I'm presuming it's a quadratic function. And then we have all of our constraints, right? So the first one is that the reference, we'll set one of the buses to be a reference angle to 0. The next constraint is the power balance constraint, nice complex form. And then the third and fourth constraints are Ohm's law plus the power definition occurring on each line. You're probably familiar with the Y admittance matrix, that's where it comes from. And then the last two are flow constraints. The next slide is just a more projected onto real variables version. Does anyone have questions about the notation I've used here or what it means? Okay. Now, I would say the default way to implement this is that we represent the voltage variables in polar coordinates, and then we represent all the other variables in rectangular coordinates, in particular like the admittance on the lines. And if you do that, you end up with a version of the mathematical program that looks like this. We have our quadratic objective function. Now we're using, like in this version of the model, we use PG to mean like power generation, active power generation. We use QG to mean reactive power generation. And now you can see that we have two versions of the power balance constraint because we're doing it once for active power and once for reactive power. For the line flow, we have two versions, one for active power, one for reactive power. Now, I come from this optimization background, so what really interests me is what type of mathematical program is this? What type of algorithms can we use to solve it? If you look carefully, you'll see that all of these constraints are linear or quadratic. So that means there are certain algorithms and solver technologies which only support linear and quadratic constraints. But these ones are the really interesting, challenging ones. So the power flow equations in the AC network is where you get like magnitude, like all the complexity. So you have a product of three variables, right? VI times VJ times cosine of some other variables. And you have these transcendental functions, cosine and sine. So that's why this is super interesting from an optimization standpoint. And for the beginning part of my career, I was very interested in how can we solve AC OPF better. That's where much of my research was. Now I actually am kind of giving the power community's insights on AC OPF to the optimization community. And we've discovered that AC OPF is actually an incredible benchmark problem for the optimization community as well. Why is that? So first, it's a high-stakes application. If you could solve it better, faster, more accurately, you can easily save millions of dollars annually. You can scale it to really large problems. It's very easy to make an AC optimal power flow problem with 1 million decision variables. The standard benchmark libraries for nonlinear optimization have like 100 to 1,000 variables, so much, much smaller. It has a sparse structure that comes from the fact that it's on a power network. And some solvers we've found in some modeling layers are good at exploiting sparsity, others are not. And if you want to solve large AC problems, you really need to scale to large. You need to take advantage of this sparsity to do that. And then the last piece, which is kind of going to lead into the next part of this talk, is that these derivative, like because you have in this version of the problem cosine and sine, when you take the derivatives to compute the Jacobian or the Hessian of this particular structure, the terms don't go away. So normally, like if you have a polynomial and you take its derivative, you get smaller and smaller polynomials, right? But when you take the derivative of sine, you just get cosine. So now you start having more and more terms in this like high order Jacobian Hessian. And that actually presents a number of interesting challenges for optimization technology. So overall, this has proven to be an amazing benchmark, not just for the power systems community, but like also for the optimization community. So if you want to solve these types of problems, what options do you have out there? There is a number of free open source tools. So probably everyone knows MatPower. I think that's the most famous one. PowerModels is what we've been building in Julia. There's a tool in Python called GridOpt. There might be some other ones. That's the one I know. And then there's also a not well-known tool in C++ called OPOMO, which was built by one of my colleagues at Los Alamos named Hassan Hijazi, based on a modeling layer he developed called Gravity. And we'll talk more about that in the next section. For benchmarking these types of problems, we've got pglib, optimal power flow. It ranges from 3 to 30,000 buses. Network data, so you can get up to those realistic sizes. And it's really great because you can go from those toy models all the way up to kind of industry scale and figure out where your method lands. So that's the introduction to the math of AC optimal power flow. In the next section, I'll talk a bit about how you can model it in Julia and Jump. Any questions about modeling AC optimal power flow? Yep.
So sorry, I'd like to know, compare with DC OPF, one of the AC OPF disadvantage is it will make the computation amount is slow. So they will increase the complexity in the computation. So I'd like to know whether we can use the AC OPF to solve a total degree map from a real country, use the real data currently. Whether the computation ability for PhD students papers, we can use some AC OPF to solve the program, use the real data from real world, for example, solve the transmission planning for a country like UK, Ireland, some country like
So I'm not sure I fully understood the question, but I think what you're asking is like, with these tools, can you really solve real country data? So my experience is that these tools are as good as it's going to get. So if, they're state of the art, right? So if a commercial tool is currently solving that country's data in an operating room, these tools should be able to solve it as well. In research, we'll often try to push the boundaries and solve a bigger problem or more time steps than anyone has ever solved before. And I think that's a good research challenge. But you've got a great foundation to start with here. My experience has been that actually getting the data, the real network data from a country, is the hardest problem, not the algorithm to solve it. And then when you get real industry data, you also, usually there's a lot of problems in it. Like there's errors in the data where if you do a power flow study instead of an optimal power flow study, it's very often that you can have violations of the constraints in the network, like either the voltages are too high or too low, or the flow over one or two lines is too much, or somebody entered a bus shunt parameter in the wrong scale. And what I find is that when you get realistic data, the very first thing you have to do is just clean it a lot to get it into like a research level quality that then you can go and do your performance studies. So that's why I'm trying to teach you this stuff. It's like, I think it's ready to go. Any other question? OK. So if you want to solve the types of AC optimal power flow problems I showed you in the last slides, you have a bunch of different tools out there. You know, there's GAMS, there's Ample. Those are kind of the oldest modeling tools out there. For open source, you've got things like Pyomo and Jump, and I mentioned Gravity is kind of this lesser known one. In our group, we have been using Jump since 2016 for these for a couple of reasons. So the first one was that it's free and open source. So that means we can easily run it on clusters. We can easily give it away to folks like you. The second thing is that it had a unique set of features at the time we started using it, and it might still be true a little bit today for power system modeling. So if you want to do AC OPF and DC OPF and SDP relaxations of the AC OPF, then there was no modeling layer that could do all three of those things at the same time when we started using Jump. Jump was the first one that could do semi-definite program and nonlinear programming and linear programming all in the same modeling layer. So you combine that with the fact that it could scale to realistic problem sizes, and we were definitely excited to use Jump for our research. Now that's back in 2016. In the last 2 years, LANL has gone in a big collaboration with the Jump developers to actually improve nonlinear optimization in Jump and give it like a lot more features. And these features, I think, actually are a great benefit to power network modeling, especially if you do AC. So we've rebuilt the Jump nonlinear optimization layer from scratch. So if you used to use Jump, you really need to check out. If you used it in the past, you need to check out the new version. The new syntax matches everything, so there's no @nl anymore. So it's very easy to use. But the things that are really interesting for optimal power flow are that we have support now for complex variables and constraints, which will make your modeling life a lot easier. And we have new support for derivative computations. So I will show you why these are so important. So these have made AC optimal power flow modeling in Julia a lot better, but they also have improved. It's great for other infrastructure networks as well. Going along with that new improvement of Jump, I also started a project which I call Rosetta OPF. So you may know Rosetta Code. This is a thing online that helps you learn how to code in new programming languages by showing you examples from other programming languages. So in Rosetta OPF, I basically implemented a simple version of the AC OPF problem in a ton of different modeling layers so that people can see what it looks like in different modeling layers and learn how do you go from Pyomo to Jump or vice versa. And also just to benchmark the performance of all those different modeling layers. So I'm going to show you a little bit of what it used to look like before. So I introduced for you this mathematical optimization. This is the polar form of the AC OPF equations. And I'll show you what the Jump syntax looks like for implementing the polar form. And this is the way we've had to do it since kind of the inception of Jump. So for defining, say, the power generation variables, we have to specify them in real coordinates. So we have PG for the active power and like QG for the reactive power, and then they're going to be bounded within some range, which is defined by the Pmin and Pmax type of data parameters. Then when you want to go to define something like the power balance equations, you end up with these types of things. So like the first line, so we're going to do @constraint. That's the Jump syntax for adding a constraint to your model. The first line sums up all the branches. What is the power flowing in from the branches? And whatever that is has to equal the generation minus the load minus the shunt contribution on the bus, or on that particular bus. And we have two of these because one is for real and one is for reactive. And then when you go to the line flow constraints, right, things start to get really ugly because you have kind of hidden here. Let's see. Is my mouse? OK, yeah. So you can see, right here is the variable. That's the decision variable, voltage magnitude squared. Here's another decision variable, like voltage magnitude from to times cosine of some angles, right? So these are the decision variables. The rest of this is all data processing to get the coefficients correct. But we end up having 4 of these equations because you've got active and reactive on one side of the line, and then active and reactive again on the other side of the line. This all works very well, but it's kind of verbose. Wouldn't it be nice if we could model our optimization problem in this complex form directly? And this was a very recent feature that was added to the JUMP ecosystem. But now you can define variables in the complex plane and constraints. So here, the generator now, instead of having 1 generation or 2 generation constraints, we have 1. I'm going to call it capital G, where the lower bound is now a complex number. So P min plus P min or Q min imaginary, right? Times IM is how you do the imaginary constant in Julia. So now I have my complex variable for generation. That allows me, if I generalize it to all the different data parameters, to have a complex form of the power balance constraint, where I have the complex exchange of power on the lines, generation. Here's the load, which I'm turning into a complex number so that the math works out. And there's the shunt component. But I think the real win in the complex modeling is actually these line flow constraints. So now I can define that the complex power on the from side of the line follows this particular expression. This part, so V from times conjugate of V from, right? That's the decision variable. And here we have V from times conjugate of V2. That's the decision variable. And the rest here is the data processing. But you can see it follows pretty much exactly what is written in this mathematical form. And all of the projection from that nice expression into all those more complicated expressions you saw on the last slide is handled by the modeling layer. Pretty cool. So this is a new feature. We're pretty excited about it. The other thing, which I'm going to show you the syntax here, and then I'll explain to you why you want to do it next, that we added is this new way to do differentiation. So if you've studied how to do power flow or optimal power flow from scratch, you know that computing the Jacobian matrix or the derivative of the power flow equations is a critical part of how that algorithm works. Under the hood in JUMP, you have tools that compute those derivatives for you. That's how you solve the nonlinear optimization problem. But there is a specific algorithm and method that goes along with those tools. Up until very recently, that was fixed in JUMP. You only had one choice. You had to do that derivative computation the way that they specified it. But we've generalized JUMP in a way that now you can come with your own method for computing derivatives and specify it as part of the solver's tools. So the one I'm going to tell you about is called math opt symbolic AD. And to use that, first you need to import the package, and then you just need to set this solver attribute that's like the automatic differentiation backend should be the math opt symbolic default one. So with just these 2 lines, you can actually change how you do differentiation in JUMP. Now, why would you want to do the differentiation? And this is the introduction to the last part of my OPF talk, which has to do with improving AC OPF solving speeds. Any questions about the JUMP modeling before we go into that? Yep.
So when you use the computation, the modeling part, it seems to me that there may be many choices before like sending the problem to the solver. So is it by default like the polar representation that is used, or you can choose it?
This is a great question, and I should have mentioned it. So when you have a complex form of a mathematical optimization problem, it doesn't specify or should you represent this variable in a polar coordinate system or a rectangular coordinate system. By default in JUMP, it's always rectangular. So there's actually no way to get the polar form that we might want unless you write it by hand right now. We're still trying to figure out if there's a nice way to support like the user specifying how the projection should be done of the complex variables, but the the easy thing to do is just to say it's always rectangular, which is maybe not ideal for AC power flow, but it works, right? If you can solve the rectangular form of the power flow equations, it works just fine in IPOpt. And that's what you'll get from jump if you write it the way I showed you. Yep.
Still about the exponent, is there any numerical advantage, or is this just a change in the writing?
So the question is there a numerical advantage to the complex form? The short answer is right now, no, because it's just a modeling layer trick. So you get to write it in complex form, and then jump will translate into real numbers and send it to the solver. There's a very nice theoretical work from Cedric Jose and Dan Molzan from some years ago that said, if you had a solver which natively supported complex numbers, you might be able to save a factor of 2 or more by just reasoning over the complex math directly. But right now, no solvers support that. So jump has to send it in a real form. But supporting the complex modeling in jump is the first step towards, like first people have to write the examples, then we need the solvers, then we'll be able to have both benefits. That could be a good research project, like taking a complex version of the power flow and getting it into an algorithm directly without having to project it down. I know folks at RTE were working on that some time ago, but I'm not sure where that stands now. Okay. All right, so the motivation for this differentiation computation stuff has to do with what is the current state of the art in AC optimal power flow. So my good friend and colleague, Hassan Hijazi, he maintains a modeling layer in C++ called Gravity. And he showed these results a couple years ago for runtime performance. So what do you have in this plot? Instance numbers are like all the pglib benchmark problems. And then he's showing how much slower each other open source tool is than his Gravity solution. So the fact that all the bars are high means that everyone is slower. He said power models, but really what it means here is jump. So modeling it in Julia was slower. And I would say, like, if you kind of cut the line right here, he tends to be about 2x or 3x faster than the state of the art when you just like try to do your best. And the thing that we dug into this in a lot of detail when we were doing the nonlinear modeling layer rewrite in Julia, because we wanted to make sure we could close this gap if we're redoing everything from scratch. And the thing that was really surprising was that there was actually an algorithmic insight to this. It wasn't like, oh, he just made his C code much faster. It actually had like a very different approach to how to do things. And that was super interesting. So in this context, we were looking at not just AC optimal power flow, but like all modeling of nonlinear optimization. So you have like some functions which are kind of polynomial in structure. Maybe they have transcendental functions too. And we're just interested in like how can you solve these really fast and at scale? I mentioned before you have these different choices of modeling layer, but what you need to understand is that the way this class of optimization problem is implemented is very different than, say, linear programming or conic programming. And it's for the following reason. You see at the high level, just like I write my nonlinear optimization model and then I send it to IPOpt. That's like your interface to the world. But actually what happens is that the way IPOpt and Nitro are built is that they have a particular NLP algorithm, but they need the modeling layer to produce them oracles for the Jacobian and Hessian. So essentially, like the IPOpt algorithm is just like the NLP piece, a linear solver subroutine, and then it has to call this Jacobian and Hessian oracle, which is built by the modeling layer. So the modeling layer has the job of both helping you write a beautiful mathematical program, but also producing efficient code for computing Jacobian Hessians, which it sends to IPOpt. And so that is the area where you could potentially improve IPOpt without actually having to change the source code of IPOpt. So how does one of these modeling layers do the Jacobian Hessian computation? essentially I'm just going to use a toy function because the AC ones are kind of big and gnarly, and you can understand it from this simple example. Imagine you want to compute derivatives of this function, product of two variables plus sign. The default implementation is a thing called automatic differentiation, either in a forward or reverse direction. But essentially, what you do is you break the mathematical expression into a tree, and then as you evaluate the leaves of the tree, you also keep track of the derivative of that evaluation, right? So as you go through the tree, if you just have a second variable, like a separate piece of data, which is, well, the derivative so far of this tree is like this, and every time you go over an edge, you just compute the derivative of that function. When you get to the top of the tree, you have the evaluation of the function, but also the evaluation of its derivative. And this has been very effective. It's the default approach. I would say in the optimization community, many people thought there was nothing better to do than this. One obvious optimization you could do for this is if you know your function is linear, the derivative is a constant. If you know it's a quadratic function, the second derivative is a constant. Those are like easy optimizations you should make. But there's a more sophisticated one, which I'll show you. A natural thing that many people would wonder is why don't you do symbolic differentiation, right? Before we start solving our optimization problem, we can say, well, let's just use an arithmetic algebra engine to compute the derivative of this, and then we'll know exactly what it is. But this can be really time consuming. So imagine you have 10,000 constraints in your problem, which is the case for AC optimal power flow. You would have to do this symbolic computation 10,000 times with different data. That would take a lot of CPU. And if you just throw a symbolic engine at a problem like AC OPF, you will see it just takes forever. So there's no hope. So what was the insight of gravity and that Hassan had, really? And it was basically the following thing. You can represent your constraints as templates, right? So I showed you in the beginning of the talk how in Power Models, you kind of loop over all the branches and you say, add this type of constraint, 10,000 times. If you know you have that structure, the constraints have a consistent structure to them. And you can do the symbolic differentiation for one of the templates and then reuse that with different data over and over and over again. So so if you have a function that looks like this, you can think that some parameters are data, like PA and PB are data, and AX and AB are the variables. You can compute a generic derivative for the variables, XA and XB, and then plug in different data, PA, PB, over and over again with that generic thing. And I guess the first insight was okay, there are, you can do this kind of symbolic thing when you separate it into variable and data. But the other key insight was that most nonlinear programs have repeated structures like AC OPF, and you can really exploit this in many contexts. So if we look at the AC optimal power flow problem I showed you before, there's really only two non-trivial constraints for computing the Jacobian and Hessian, right? Because if it's linear or quadratic, you can just kind of fix those at the beginning of the solve. And so if you only need to compute once the symbolic derivative for an expression like that, and then you can reuse it for all of the power flow constraints in your model. And I showed you before this MathOp symbolic AD. This tool does exactly that. It takes a different approach to computing derivatives in your problem by analyzing the constraints and then making these symbolic derivatives in Julia for you. So let's see what it does performance-wise. So we're going to benchmark a bunch of different solvers on AC OPF and see what happens. For the experiment, we're going to keep IPOP the same. We're going to use a fast linear solver, MA27, and keep IPOP the same. And the only thing we're going to change is how we compute these derivatives. I'm going to use the 54 base case instances from PG OPF, PGlib OPF. They range from 3 to 30,000 buses, which turns into like 10 to 200,000 decision variables. For jump, we'll compare the default reverse sparse AD system to the new symbolic AD system. And for reference, we'll also include a couple other modeling layers. So we have ample, which is they have a format called NL, nonlinear optimization. We'll use that to reference as ample solution for AD. We've got Hassan's tool, Gravity. And then we also had a tool called Casati, which is a popular AD system for control systems, just to give us different reference points. So let's have some results. Let me see. Can I get my cursor back? OK, there's. No, I think I can't find it. Oh, maybe there's a laser pointer. OK, cool. All right, I will point over here. So this is just the total time you spend in the AD library for jump in AC OPF using the reverse AD system in blue, and then the symbolic approach I just told you in pink. So the thing that's really awesome is that for the largest data set in PGlib, this gives you a 4.5x improvement in time you spend computing derivatives over the full solve. So that's really, that's a dramatic and a fantastic jump. Now, unfortunately, that doesn't translate exactly into the total runtime of your OPF problem because you do more than solve derivatives, right? You have to solve those linear systems too. So this is the runtime, not the AD solve time. And you'll see that now the gap is, it's only a 1.75 increase. But I can tell you I studied AC OPF a lot. A 20% increase was challenging. So to get like a 170% increase was really excellent. So this is awesome. That's Hassan's big insight into solving these problems. If we look at other symbolic systems or other ways of solving AC OPF, we actually learned a lot of interesting things here. So let's see. The blue, let's say brown is if you use that NL interface. So that's like the amples system for computing derivatives. And light blue is Casati. So that's the other kind of AD system we had handy. So the first thing is that jump's default and Casati are very similar. So you'll see like these two points are kind of close together. So they seem to have very comparable reverse AD systems. Casati is considered to be a state-of-the-art system. So it's cool that jump's original AD was state-of-the-art. But also this NL tool at large power network sizes is actually pretty impressive, like how fast. It's very close to the symbolic AD system in terms of its performance on large power networks. So there's something interesting going on in ample that we don't understand either. But the big question is, are we beating gravity? Did we close this 3x gap? And to show you very specifically, jump's default is about 3.5x slower than gravity out of the box. And with the symbolic AD, we closed it down a bit more. So we're not 100% there yet, but it's a lot better than it was before. So this is a pretty big and exciting feature if you're solving really large AC problems or other large nonlinear problems in jump. Just try the symbolic AD library and see if it makes your problem faster. Now, we use it for all of our large-scale stuff in infrastructure. This is almost the end of this talk. I just wanted to mention one more interesting development. If you're interested in large-scale optimal power flow things, there is some very nice new paper by Shungo Shin and other collaborators at Argonne National Lab, where they got AC optimal power flow to work efficiently on a GPU. And I think this is now the new state of the art for like absolute fastest AC optimal power flow solve times. You can see, like, if we look at the last row here, this type of problem usually takes about 5 minutes to solve. under like this particular circumstance, they got it down to like 100 seconds. But with the GPU implementation they have, they got it down to about 16 to 20 seconds. So it's pretty rare, I would say, that you actually see a substantial improvement in AC OPF solve times. At least that's been true for the last decade. And now we've seen two really nice improvements back to back. So we had one that came from Hassan's insights on symbolic differentiation. These tools use a similar system. And then cracking this problem of like, how do you get AC OPF to run on a GPU has been a grand challenge that many have tried, myself included, and pretty much failed. And I think it's an incredible achievement that Shungo and folks got that to work finally. So you should check out that paper. It's super interesting. So with that, I'll conclude this part of the talk, and I'll just say that AC Optimal Power Flow is super awesome. I hope you love it as much as I do. Oh. Let's take any questions you have about this talk, and then maybe a 5-minute break after that.
Baseline because I saw a comparison with Opomo, but I think it's C++ and Julia. So
yeah. So the question is, we compare to Python. Opomo is in C++. We have in the Rosetta OPF ecosystem, we have a couple of Pyomo implementations, which you can go check out. One of the challenges there is that Pyomo writes NL files. It doesn't have a direct memory interface to the solvers. So it's kind of capped. It can be as fast as the Ample study I showed here, the NL file, but it can't be faster because there isn't, all it can do is write the NL file and then it can't change the AD system. So for large problems, writing the NL file is not a big overhead relative to solve time. For smaller problems, it is. So it really depends on your use case, how viable it is. There's one in the back. Yeah. Yeah.
I guess what's the difference in the instances where it performs well versus badly, and do you know why that's the case?
Okay, so that's a good question. The question is basically, why is jump so bad, like in this regime? And the short answer is that it takes a little time. Like there's a small constant overhead we're using jump. Like maybe it's 1/10 of a second or 1/100th of a second. And because Opomo, which is based on gravity, is a compiled C code, there's like no overhead to start. So really what you're seeing here is like as the problems get smaller, that overhead plays a bigger role. But once they get kind of I would say, interesting size, non-toy problem size, then it's stabilized and you have a consistent 2x overhead or 3x overhead. So yeah, this has never been particularly worrisome to me because most of the challenging problems I encounter are like big OPF problems. But if your code needs to solve like, I don't know, 1 million tiny OPF problems, this you would care about. Other question?
Do you have plan to have a Python version of your tool?
Is there a plan to have the Python version of the tool? No, and I think inside the jump community, which I'm involved, we often think like, is there a good reason to rebuild jump in Python? Because then the user base and the ecosystem would be so much bigger. And we keep coming back to the answer of like, no. And I think it's because the tooling around Julia is so good for like distributing the solvers and like getting the libraries to work on all the different languages or all the different operating systems that we don't see a way to do it easily in Python. Another advantage of Julia, I didn't really talk about it, is that when you write a function, it gets compiled down to source code. So it's really fast by default. And there isn't kind of an analogous solution in Python. You have to use a library to like help you get performance. And so that's another challenge. Is like we'd be building like a mini Julia inside of Python. So like, why don't we just use Julia? You can call Julia from Python. That's so Panda Power actually for OPF. There's a way you can call power models because they find that the power model solver is good enough. It's worth doing that. Other question? There's one back there.
So back to this, say for smaller networks, there is like a pre-compilation overhead in Julia.
I don't think maybe it's a little bit of pre-compilation, but there's maybe some other overhead, like dynamic library starting or something like that.
Would that impact the performance in real time series kind of workflow?
It's just on the first call. So like in this experiment, you're running one OPF problem from the command line, and then you're terminating. So there's like, if you had a loop inside of Julia, you would pay the overhead the first time, but not the repeated times. Yeah, so it really depends on your use case, how much this will impact you or not. Yep.
I have a question about the symbolic translation.
Yeah.
When you put some constraint in jump, you can either do it with a for loop, so externally, so for and then add constraint, or you can vectorize it. When it is vectorized, is it easier for the differentiation tools to detect the structure through it?
So the question is, depending on how you model in jump, does the system have a better time detecting the constraint structure? And the answer right now is it doesn't matter. And that's because the constraint structure detection method happens after all the vectorization has been expanded. So it's like a modeling tool for you. You can write vectorized, and that's very convenient. But like by the time it gets to the lower levels, it's all been flattened because that's what the solvers expect to see. Right now, there's no hint procedure for the symbolic AD system, but we actually don't think we need it. I mean, it can, on a huge power network problem, it can detect very quickly. There's only two canonical types of constraints. So I think the challenge with that library is more like if you have really big constraints, like with thousands of terms in them, which is not the case in AC optimal power flow, the analysis can take a lot of time. So yeah, it's definitely not for every problem. The reverse AD system works well for many applications. It's just these network ones, symbolics is actually kind of good because they have that structure of very small constraints repeated many times. Yep.
Like, how you put in.
Yeah, I use IPOP for most things. I mean, it really depends on your application. If you're doing MIP, we use Gurobi usually. Highs is a great open source alternative. Yeah. There's one here.
Also, quantum solver in your ecosystem?
That's a great question. Am I working on any interface for quantum solver? I am not. There is a different set of folks who are working on something called Cubo.jl, which is kind of like Jump for discrete optimization in Julia, but like also targeting quantum and non-quantum things. So I think there's some people thinking about this, but the hope would be one day someone has like a quantum thing that can solve mixed integer programming. And then we can just like tell Jump to target that mixed integer programming solver, and the interface will be the same. It'll just also use a fancy piece of hardware to do it. Okay, everybody, we're back. I hope you're well rested because now the stuff gets really crazy. So I'm going to try to give you a brief introduction to quantum computing, and let's emphasize the brief. You know, like it takes a semester to learn quantum computing, but we'll try to give you the most important pieces in the next 90 minutes. So you may have heard, but the quantum computers are here. Right? It's a very exciting time to be exploring quantum computation because after decades of being promised these things, we finally have computers we can play with and try out. One very important milestone that was hit in 2019 was this Google quantum supremacy paper. What did they show in that very newsworthy paper? They showed that there was a particular type of contrived computational task. It was sampling from a very peculiar type of distribution where a quantum computer, their quantum computer, could do it much, much faster than even a supercomputer. So like a cluster with thousands of nodes in it. So that's very exciting. Like, that's a great achievement. However, I wouldn't say that the world has dramatically changed or computation has dramatically changed since that result happened. Right? There aren't. It's not immediately obvious how you translate that contrived problem into a real impactful application beyond maybe random number generation could be one good application that I imagine from that particular result. On top of Google, there's actually a lot of different companies working in quantum computing. I'm showing an infographic on the right from Domain of Science, which is a really great science communication person named Dominic William. And he made this infographic. In this picture, you see each circle is a particular quantum computer that is on the market or has been announced with a number of qubits on the inside of it. This is somewhat old. 2 years old is like ancient history in quantum computing time. So there's many more now. And every line of text in this image is a company that's working in quantum computing. So there's just a huge number of people working on this, and it's a very exciting time. Now, the first important thing to know about quantum computing is that we are currently in an era which is referred to as noisy intermediate scale quantum, or NISQ. You hear the term NISQ a lot. And really what that refers to is a particular time in this technology's development where things are very just beginning. So here's a picture from 2018 that Google put together to explain their quantum research roadmap. On the x-axis, you have number of qubits. That's a logarithmic scale, so that's growing really fast. On the y-axis, you have the error rate of these qubits. With our computers we use every day, we just presume that they're errorless because they have error correction built into them. Quantum computers currently do not have error correction. So you have physical devices that are analog in nature, and they just have errors from the external environment. What Google was charting is that over time, they were expecting the error rate of their qubits to come down. Simultaneously, they would grow the size of the qubits. And the kind of purple areas you see here are not particularly interesting from a computation standpoint because they indicate areas where a current classical computer can simulate what the quantum computer does, usually faster than it could do it itself. But the interesting regions are ones where we get a lot of qubits or very low error rates, because then we can start to do things with quantum computers that no classical computer can do. The green area, so that's they projected in this figure like around 1 million qubits with error rates of 10 to the minus 4, is where we know for sure there are useful quantum applications. So we have algorithms, they've been proved to be correct, and if we had a computer that big, we would be able to solve them. I think the interesting thing is the blue area that is very close to where we are now, where we're in a regime where we can do some things that classical computers can't do, but we don't have beautiful proofs that there's an application there. And that is really what is being said when people say noisy intermediate scale quantum. They're talking about the blue area here where no one really knows if these computers can be used for something or not. Now, looking at current technology you can buy or get access to today, we are approximately here on this roadmap. So we're at about 100 qubits to, like, let's say 1,000 qubits, but they're not at an error rate which is below the threshold for quantum error correction. So we're like close to the dash line, but kind of bigger than expected in this roadmap. Now, what does it mean to be here? I would say the experience I have is that these computers are just barely working, right? If you've tried to run something on a quantum computer, you will have experienced failure. Like by default experience is you try to do something, it doesn't work, and you spend hours and hours debugging the computation, understanding the quirks of your specific vendor's hardware, and then over time, you can start to get like glimmers of hope that these computers could be really interesting and useful. And that's why I'm still working on this, and that's why I think many of you may be interested in it. But I think every paper you see out there that presents good results on a quantum computer, you should believe that that was a Herculean effort to get those results and not like something that comes easily. The thing that has generated a ton of excitement in the last year is that a number of hardware vendors have suggested that we'll get to approximately this green spot by 2030. So 6 years from now, we may be in a regime that's dramatically different for quantum computing than we are in today. So that's pretty exciting. We'll see if they can make it. It seems like, to me, that sounds like a dramatic technological progression in a short amount of time, but they say they can do it, so we better get ready. What is it like for, to use quantum computers today, especially at a place like Los Alamos? I think it's very similar to this picture of Grace Hopper and other folks around the UNIVAC in the 1960s. There's a really expensive new piece of technology, and we're all sitting around it being like, what is this doing for us? Especially we're interested in how fast does it go? Is it going to beat what we can do on our classical computers? And to be really blunt, I would say we're really wondering, are these going to be good for anything? Because it's maybe, there's a lot of excitement around quantum computing, but once you start to dig in, what are we really going to use these computers for? It turns out the applications are kind of hard to articulate. So I think quantum computers are going to be useful, but it's not as trivial a question as many people might expect. So we're sitting around the quantum computer, we're wondering, what is it going to be good for? What are the killer apps for quantum computers? On the right, I'm showing some examples of different quantum computing technologies. The top one is a trapped ion system. The middle one is a vacuum chamber that would be used for an atomic system. And the bottom one is a superconducting chip. They can all have different pros and cons we'll talk a little bit about later. But the question of what are we going to use these for is the short answer to that is simulating quantum physics. So you have a lot of applications that come up in materials and chemistry where our current classical methods and algorithms are totally inadequate for what we want to do, and the only clear path to having an adequate computer is a quantum computer. This is, I think, in energy systems, this could be things like designing batteries. How batteries work, how different storage technologies work. It could be designing materials for different aspects of energy systems. But yeah, simulation of quantum physics for materials and chemistry is the easy, obvious application for this technology. But this is a power systems summer school, right? So the important question for today is, will quantum computing change how we do power systems? And my most honest answer is, I don't know. So I'm going to teach you a bunch of stuff, and let's talk about it more during the breaks. I'm still working in this area, so I think I think there's hope, but it's definitely tricky. So that's the introduction. For the rest of the talk, I can tell you for sure I have more than 90 minutes worth of stuff. So we definitely aren't going to get to all of it, but I've put it in this order because I think it's the most valuable. So first, I'm going to talk about the mathematics of gate-based quantum computing. That's the bulk of the technical content. And the goal here is really to give you the foundation you need to go and read a paper on quantum computing and understand what is going on. Even if you want to read some of the ones that are published in power system venues, you're going to need to know what I describe here. I'm hoping that this will let you fill in the gaps and be able to read those papers. Then in part 2, I do a brief overview of the state of quantum computing hardware as I see it today. Part 3 is some discussion of quantum computing and power systems. This is a very early stages for that field, so there's not a great amount to review. And then part 4 is all about quantum computing and optimization. I strongly suspect we won't get to part 4. But let's try to get through part 3, because I think that's the most useful for you all right here. Okay, so let's talk about the mathematics of gate-based quantum computing. I will say that all of these slides I developed in collaboration with a close friend and collaborator, Gakumo Nanichi. He has a wonderful paper in the SIAM review called An Introduction to Quantum Computing Without Physics. So this is heavily inspired by that review because it is a way to get introduced to this field without needing to like learn a bunch of quantum mechanics. I also, many of these slides, developed them with a collaborator of mine named Mark Voufray. He's a physicist and computer scientist jointly, went to EPFL for his PhD. And I always find it's really helpful to have a physicist look at any quantum work that I do because they have a different perspective on it than me, and it helps me like kind of balance the physics part and the computing part, which I know better. And I would encourage anyone working in this area to have collaborators in other fields. It's really interdisciplinary, and it helps give you a well-rounded perspective. Okay, so what is the most important thing to know about the mathematics of gate-based quantum computing or quantum computing in general? This introduction I'll give you for like 1 hour is mostly about notation. You are all capable of understanding what this quantum computing model is. It's basically linear algebra over complex numbers. And I know you know both of those because that's an essential part of power systems. The thing that makes it really difficult to understand is that there's a lot of specialized notation that comes into this community, which makes it like really hard to follow what's going on. I will teach you all the notations in this talk. So it's not bad. Preliminaries. This is the mathematical foundation that you just need to believe me on faith that these are all reasonable things, but they're not that bad. So the first thing is we're going to be on complex numbers. That's the foundational numerical value of a quantum computer. I hope because we just talked about AC power flow, you remember what complex numbers are. This is really important when I talk to computer scientists because they never encounter complex numbers. You guys do all the time. So yeah, we can have rectangular or polar forms. Usually in this talk, we'll be putting it in rectangular coordinates, but a few times I'll use the polar form when it's convenient. The important thing that you do need to know is we are going to use the complex conjugate, right, where you negate the angle or the imaginary part of the complex number. But in quantum computing, we use a generalization of the complex conjugate, which is for matrices. We're going to be dealing with complex matrices a lot. And so when you want to transpose a matrix, or when you want to take like the Hermitian transpose, right? So you want to take the complex conjugate and transpose the matrix. So you can see the way I would normally represent this in the notations that we use is that you take the matrix and star it and then say T for transpose. Sometimes in papers you'll see H for Hermitian transpose, but the most popular notation that you see in quantum computing is actually this dagger, right? It looks like a T. It's like a transpose. But when they use the dagger, they mean complex conjugate transpose, okay? So that's the important point there. Why do complex numbers come up in quantum computing so many times? It's the same reason we use complex numbers for AC power flow. Quantum physics in the foundation is on waves. So if you want, and it's going to be operating in a steady state, right? So if we have waves in a steady state, a compact description of what's going on is the amplitude, R, and then a phase shift off of a nominal value. And so this is why we end up have complex numbers. This is the end of physics. No more physics. Next important structure is a thing called Kronecker product or tensor product, which we'll represent with this X in the circle. And this is a recursive matrix operation. And it's really useful if you're working with exponentially large data or information. Imagine you have a really big vector, like exponentially large vector. How can you write it in a paper? You need a way of building up a really big exponential vector. Kronecker product will help you with that. So here's the definition. So if you have a matrix A and a matrix B, you just, for every entry of A, you insert the matrix B, and then you distribute the coefficient of A, and you get a bigger matrix. So here's one particular example where I have two 2x2 matrices, and you can see that I've replicated the second matrix 4 times and then multiplied through the coefficient, and I get a 4x4 matrix. This works for vectors too. So here's an example of doing a Kronecker product on vectors and then the Kronecker product on matrices. Next, we have a thing called Dirac notation, which is also sometimes referred to bracket or bracket. This is a notation for discussing column vectors and row vectors, essentially. So imagine that we have a Euclidean space S, which is defined over n complex numbers. So c to the n, that's what I mean by c to the n complex numbers. If we have a column vector on this Euclidean space, we're going to write bar vector and then close bracket, like right angle. If we have a row vector, we're going to use left angle, then vector bar. Now, to make all the math nice in quantum computing, we're going to say that like when you change the row vector into the column vector or vice versa, you should take that conjugate transpose. So there's the dagger operator you see. So they both it looks very similar, but like one of those is very long and one is very tall. So the one where you put the left bracket and then the bar, that's called a bra. And when you put the right bracket and the line in the right bracket, that's called a ket. So now you have brackets around you, right? That's where it comes from. And so when you end up like looking at a sequence of matrices applied to these vectors, you end up with like a bunch of bars with the matrices in between and the row and the column vector on the end. You multiply that all through, you end up with one number, right? So that's kind of what a sequence of operations looks like. And of course, they're applied right to left, which is maybe a little counterintuitive, but that's how the matrix algebra ends up working out. What does this all have to do with quantum computing? Well, they define this notation, so you'll see it a lot. But these quantum computers are going to work over these large dimensional complex vector spaces. So that's why they end up with this particular notation. Now, what is a gate-based quantum computer? It has 3 key components. So we're going to have first a quantum state. You can think of that as a register or maybe like a memory, but it's going to be a thing that's called psi. And that is a particular, the state of the quantum computer that's initialized in a predefined way. And then over time, we're going to apply operations to it, which we're going to call U. These are going to be matrices. They will be specified in advance by the algorithm, and they get applied to this state psi. And at the end of the algorithm, we're going to measure the quantum state with this special measurement operator. So you start in a specific place, you apply U, and then you measure. That's basically what the quantum computer does. Now, we call this the circuit model. And it's kind of similar to a Turing machine. A Turing machine is like the theoretical model for a classical computer. And there's a number of fundamental results about this particular computing model that go back to the 80s. Now, there's another model of quantum computation called the adiabatic model, which is a continuous time model of quantum computation. And it's equivalent to this one, at least with a polynomial overhead. But I'm not going to talk about that because although it's my favorite, it's kind of less prominent in the literature. So this will be much more useful to you in general. Maybe at some point we'll have some time to talk about adiabatic model. So the next section of slides, I go through what is the state, what are those operations, and talk a bit about measurement. So let's talk about the state of the quantum computer, which is often called psi in literature. We'll begin with 1 qubit, right? If we can't do 1 qubit, how are we going to do n qubits? So a qubit is going to be, the state of the qubit will be a unit vector of 2 complex numbers. By convention, we're going to say that the standard basis for this unit vector is that there's going to be a 0 for the first entry and a 1 for the second entry. So what I'm showing you here is the vector is right there. Here, pointer. Yeah. So here's the vector. Because there's a 1 in the top, we're going to call that 0 entry. Here's the complex vector. Because there's a 1 in the bottom, we're going to call that the 1 entry. Right? Down here, we require that whatever the quantum state is of any dimension, that it's a unit vector. So the what's that, inner product is going to be equal to 1. So this actually comes back later. Everything will be normalized to 1. I like to think about it like this. So you'll often see these written like this. But this is maybe a more descriptive version of the same thing. So the first row has basis 0, and it's a complex number. So here it's magnitude 1, 0 imaginary part. The second row is basis vector 1 with 0 everywhere. This is a simple quantum state because all of the unit vector's mass is in the first entry. But of course, it can be like these complex numbers can be arbitrary things as long as it meets the unit vector requirement. So here's an example where the state is split between the 0 basis and the 1 basis. So it's split between those two. And you'll see that I've used these square roots because then when I do this product, it sums to 1. So it's very often that you'll see like a square root here, a square root there in quantum constants. And it's all about getting this normalization factor right. Let's talk about reading the quantum state. So when you read a qubit, you're going to get a basis state, 0 or 1, not that complex number, the two complex numbers. So it's like, that's a big thing. You only see the basis states. So it turns out that the amplitudes of the complex numbers are the things that determine the probability of which basis state you observe. Let me go slowly through this. So basically, if we have a quantum state, we take the outer product, which gives us a matrix. Then we look at the diagonal of that matrix, and that gives us probabilities. Probabilities determine what we're going to see when we perform the read operation. So let's go back to this example. So we have a square root of 0.5 probability on the, amplitude on the first basis, and the same on the second basis. If I do this outer product and look at the diagonal, now I have probability of 0.5 on 0 and probability of 0.5 on 1. So when I read the quantum computer, half of the time I'm going to see a 0, and half of the time I'm going to see a 1. Here's a more complicated example, right? I can have like real and imaginary parts, like weird terms in both cases. And for this particular quantum state, I see 0 5/16 of the time and 1 11/16 of the time. So we only get to see zeros and ones, but kind of under the hood of what we're seeing is this really complex number representation of the state. The goal of a quantum algorithm is to put most of this amplitude in the right basis state. So it's like a bit vector, let's say. You could think of it as the optimal solution to your combinatorial optimization problem, for example, so that when you read the quantum computer, you have a high probability of just seeing the right vector of zeros and ones. Ask me questions about this now. This is really important. Yeah. This right here? Yeah. So these are called the basis states, and we can call them whatever we want. We could call them A and B. We could call them, up and down. There's kind of conventions in the quantum community what you call them, but usually this will just be a sequence of the numbers from 1 to 2 to the n. So integers. And our goal is to we're looking for the right integer, like the lowest energy solution to our problem or something like that. And we want to manipulate this data so that when we read it, we get some one of those bit vectors that we like for whatever reason. Yeah. Okay. Any other questions about reading? If you have an insight later, let's come back to this. This is like one of the fundamental challenges. Yeah.
In which way are we going to?
That's the next slide. Was there another question?
So we use the base, the 0 and 1.
Yeah.
And then I don't get the matrix that's next to it, so it's not. So this would be the probability that we would see the base 0, and the second row would be the probability of the 1.
Yes.
And the B is like above it say the diagonal, the multiplication of the two states. But I don't get how it was 0.5 and the probability change. So.
Well, so if your quantum state, it can be any collection of complex numbers so that the whole vector is a unit vector. I'm just telling you the formula to go from that thing to a probability distribution, right? And it's basically just you multiply it by itself. Yeah, and that's what this is saying. Multiply this number, like absolute square it, then you get the probability 0.5. Yep. Okay, so this is how it all works on 1 qubit. How does this generalize to multiple qubits? This is where the power, the excitement of quantum computing comes from. When you increase the number of qubits you have in the system, this vector grows like 2 to the power of the number of qubits. So if we have 1 qubit in our quantum computer, the vector we can reason over is 2 complex numbers. If I have 2 qubits, I can get 4 complex numbers. If I have 3 qubits, I get 8 complex numbers. So this is why we need the Kronecker product, because we Kronecker qubits together, and then we get these exponentially large vectors. But this is also the really the powerful thing about quantum computers. With a linear amount of resources in qubits, we're going to get an exponentially large vector that we get to reason over in our quantum algorithm. Okay, so let's do a 2-qubit example to show you kind of how the space grows and why it starts to be interesting. So for 2 qubits, I mentioned it before, but the quantum state, it's like 2 complex numbers. You Kronecker product a bunch of those states, the vectors together, and then you get the space of the whole system. So for 2 qubits, we have 2 Kronecker 2, which is 4 complex numbers following 4 basis elements. Now, here's another great example of how this notation is super confusing. Right? So it's like 0 equals 0 Kronecker 0 equals 0, 0 equals 1 over 0 Kronecker 1 over 0 equals this thing, okay? So what is going on here is we're going to call this basis state, the 0 basis state, this is going to be an integer. This is going to be binary numbers. Let me show you what it looks like up to 4. It becomes clear, okay? So like now if I want to represent 1 in this 2-qubit system, it's like we're going to call this 1, which is the Kronecker. This is like the binary implementation of 1. And then you do it out here. Now it starts to get interesting. We're going to call, so it's like 1 or 0, 1, 2. This entry in the vector is going to be this basis vector called 2, which is, we can write it like this, or as the Kronecker of these things, or in the binary representation. And then this one becomes 3 here. So you may see people write integers in the bracket notation, but sometimes they'll write the bit vector of the same thing. When you see that, you should be thinking, okay, we have some Kronecker products of some initial basis states. And I haven't, for space reasons, I haven't shown it, but like remember, these are complex numbers. Everything else is an integer or binary value. So a more compact, at least intuitive for me, representation of what's going on here is that we have 4 entries. We're going to call them the basis vectors 0, 0, 0, 1, 1, 0, 1, 1. That's just the binary encoding of the numbers 0 to 3. And then this will be a unit vector over complex numbers. And if it has a 1 or an amplitude of 1 in the square, then with 100% probability, you're going to see 0, 1 when you read the quantum computer. Yes, question back there.
Once we get to larger numbers of qubits, how are we supposed to know the difference between the 2 in the brackets and like the 10 in the
The paper has to be clear about it. No, this is this is one thing that makes reading quantum papers difficult, is that very often they'll adopt kind of a convention of what they're showing you, and if they don't state it up front, you have to make an educated guess. But I would say the default I run into most is that if you're going to write this, you're going to write it as a bit vector. So that's probably a good default guess. What you find is that these problems become so complicated so quickly that you don't even write explicitly the numbers anymore. You just write a symbol and say it's like has a special value. Other question? Yeah.
Or feature of the basis. Other than the, if I have, for example, a probability of 0.5 and 0.5, is there any difference if the magnitude of the basis is different, if it's larger or smaller, other than in the probability, or it's just equivalent?
I'm not sure I understood the question, because it's a unit vector, right? Like the magnitude is fixed for the whole vector, it's normalized. What you pick your bases to be is really a convention you have to pick. You can name them anything you want as long as they're unique identifiers. That's why it's hard to know what it should be on any given paper.
You know, the probability also depends on the basics in which you project the state of the vector.
Yes, the probability does, yes. So you get to pick the basis, right, that you project on. And that changes the probability of the states you see. But they'll always be normalized to 1. Yep.
This probability depends as well on the physics of the computer.
No.
It's just algorithm.
This is math.
Okay.
Nothing about, this is the model of quantum computation. And maybe you have a deeper insight than you realize. The fact that it is normalized is one of the biggest limitations. The fact that it's a unit vector. Okay, so this is the basics of like the quantum state. But you should be asking yourself, where's all the special quantum stuff we hear about in the movies, right? Like superposition and entanglement. You know, that's what makes quantum computers awesome. All right, so let's talk about those things. Superposition, this is actually really trivial. You've already seen it, but we just didn't call it superposition. So in a quantum computer, the computer can be in a linear combination of the basis states, right? So if you observe the system multiple times, sometimes you see one basis state, other times you see another basis state. So this particular state, which you've seen so far, where we just split the probability of seeing 0 and 1 equally, is called a uniform superposition state, because the probability that you see any given bit vector is the same. It's like if you just draw every bit uniformly at random, this is the distribution you would see. Now, you can have, of course, more complicated and interesting superposition states. So in a real quantum algorithm, it's probably not going to be split 50-50. That's really kind of not useful. It's easy to generate this distribution with a classical computer. But you will have a vector with a kind of weird values for the real and imaginary parts, and then you'll get a very non-trivial distribution over the quantum states. And if you remember at the beginning, I said, you know, Google's big result was that they showed a quantum computer could sample from a distribution that it was hard to sample from with a classical computer. It's exactly this. They prepared a quantum state that had like a very unique structure so that this probability distribution would be hard to produce with a classical computer. That's all superposition is. It's that easy. Okay, entanglement. This is more interesting. Okay, so a quantum state which cannot be expressed as a Kronecker product of other quantum states is called entangled. To try to give you an intuition, what does it mean if you're, you can't be represented with a Kronecker product of other states? It means that when you observe, or like the value of 2 qubits in your system are correlated. So if you observe one of the qubits to be a 0, maybe the other one has a high probability of being a 0. If you observe one to be a 1, the other one has a high probability of being 0, well, of 1, or vice versa. But there's like a correlation between them. Here's the the traditional example of an entangled state. So it's called a Bell pair. It's sometimes called the maximally entangled state. So here we have 2 qubits. Clearly, by the definition, you can't do entanglement with less than 2 qubits. You need them to be correlated with each other. You need something to correlate with. So here we put 50% of the probability in seeing the 0, 0 state and 50% of the probability of being in the 1, 1 state. Because it splits like this, if you read a 0 on qubit 1, then you know you will also have a 0 on qubit 2. See how they're correlated? And if you read a 1, you know on qubit 1, you know you'll see a 1 on qubit 2. So this correlation in the information is what's called entanglement. I said that what is the definition? It can't be a Kronecker product. Kronecker product basically means that the 2 quantum systems are independent of each other. They're like conditionally independent. So it's kind of like, all the interesting stuff happens when you start to entangle qubits. And essentially what this claim means is that with these, like, if you pick C1, C2, C3, C4, C5, C6, C7, C8, any way you want, and then you apply that Kronecker operation I showed you before, there's no way of generating this state. It looks like that should be possible at a first glance, but it's actually pretty easy to show. There's no way to do this. So that is really where the magic of quantum comes from. You have the exponential growth of the size of the system combined with the fact that you can do these kind of correlated operations. So those are the ideas of superposition and entanglement. So how can a gate-based algorithm be faster than a classical computer algorithm? I'm showing on the right the picture of the complexity classes of computation. So essentially, the key thing that a quantum computer gets you that other computers don't is this huge amount of space to work with, right? So we have a vector that's exponentially large in the number of qubits. The class of computations that allows you to do is called BQP. So that's a quadratic, like a quantum polynomial time problems. And the interesting thing about this BQP complexity class is that it doesn't include NP hard problems. So that's like hard optimization problems, or I should say NP complete. It does not include NP complete problems, but it does go into this complexity class called P space, which is like one where you have a huge amount of space. The boundary is still a subject of computational theory. But if you want your quantum computer, your quantum algorithm to be really useful or faster than classical, you should exploit the fact you have this exponentially large space, and you should manage the properties of superposition and entanglement very delicately to take advantage of them to get a shortcut in your computation. If you don't leverage those properties, most likely there exists a classical algorithm that's just better for the thing you want to do. So that's the quantum state. Next up, we have quantum operations. Any last questions on quantum states? OK. So these things we are going to call U. So quantum operations U are called gates. These are going to be square, so we call them gates. These are going to be square matrices of complex numbers that we're going to apply to the quantum state psi, right? The theory of quantum mechanics says that these operations need to be unitary. What does that mean mathematically? The complex transpose of U times itself has to be equal to itself times the complex transpose, and those have to be equal to the identity. So they end up being like kind of a normalized matrix. And of course, the quantum state always has to be a unit vector, right? So it turns out that if you have a unitary matrix and you apply it to a unit vector, you get a unit vector. Given that the quantum state has size 2 to the q complex numbers, the gates have size 2 to the q by 2 to the q. So they're square, big square exponential matrices, where q is the number of qubits. The consequences of this unitary property here is that the quantum operations are going to be linear transforms of the quantum state, and these operations are going to be reversible because you have that kind of, see how the two matrices can be changed in their order. That means that you can reverse the computation. At first glance, this should feel really restrictive, right? Like these are really tough properties to satisfy. But you might wonder, like, can you really do any useful computation with this restrictive properties? But back in 1985, it was proved that even though this looks really restrictive, it's actually Turing complete. So that means with this model, with these restrictions, you can compute everything a classical computer can compute, and then even more because it's more general than a classical computer. I'll do a simple example on 1 qubit to give you an intuition for how this works. So here's a very boring quantum state. So remember, we have a unit vector over complex numbers. In the past examples, you had 0 and 1. I can make it -1. That's totally allowed. It's still a unit vector. Now I'm going to have a matrix operation on 1 qubit, which is 1, and I get to put I down here. Remember, I'm a complex number, all allowed. So I will just visualize in this 2D plot what is going on with this quantum state. So I'll just show you what this number is doing. So I initialize the state like this, and then so it begins here. And now I apply one application of the matrix U, and you can see that just do the algebra of multiplying this state times this one. Now we get a -I here. That has this effect of essentially rotating the quantum state by 90 degrees down here. Okay? If I apply it again, I rotate it again, and so on and so forth, and I can come back around and it'll repeat forever. So essentially, like you could think of this quantum operation as just a rotation that occurs on the second basis state of this vector. And that's like ultimately all quantum algorithms are just like moving the unit vector around in the quantum space and interfering it with itself and rotating it around. That's the whole thing. So back to notations, right? So a quantum gate is going to be represented by this matrix U. It's often drawn in a score. So that is where we put each line in the diagram is going to be a qubit. And then if a gate interacts with multiple qubits, we draw it as a box on the lines. It looks like music. That's why they call it a score, right? Now, this is very deceiving notation because it looks like this U operates on 3 pieces of data, right? Like 3 qubits, like there's a U. But remember, these are 3 qubits. They have a quantum state that is of 8 complex numbers. So this U is an 8 by 8 matrix that you're applying to a vector of length 8. The quantum scores, if you have like multiple operations, we'll start with some generic quantum state, we'll apply like one matrix and then another matrix. The scores are read from left to right. It's like do this, then do this and this. But because of how matrix algebra works, you have to write it right to left. So like this quantum score would be written as psi U1, U2. Very easy to get mixed up about that. I did many times when I was first learning this. So essentially, a gate-based quantum computer program is just applying sequences of these unitary gates to a quantum state and then measuring some useful information at the end. So for the purpose of this tutorial, I'll just presume you start with some psi, you apply a bunch of these unitaries, and at the end we just read the data and see what's going on. You can do measurement. Like the model of quantum computation allows you to measure subsets of qubits in between, but I don't talk about it in this tutorial. But just know that that's like compatible with the model of computation. It's important to understand how you can apply these matrices to less than all of the qubits at the same time. So like this is the most general form of a quantum gate. But usually when you see a quantum score, it'll be like just one gate applying on 1 qubit. When you see something like this, you should try to understand what it means mathematically, right? This is, say, if it's on 1 qubit, that's a 2 by 2 matrix. But this whole system is like a vector of size 8. So like, what's going on, right? The math doesn't work out. Essentially, there is an implicit identity matrix on each of the other qubits. So when you see U only acting on 1 qubit, what you should be thinking is that I have identity chronometer product with all the other qubits until I get to the U that applies on a subset of them. And then that matrix will be the right size. That will be the 8 by 8 matrix, which I can apply to the vector of length 8. There is a generic, for 1 qubit, you can write a generic form of what all the gates are that you can run on it. That's parameterized by angles. This is the version that was adopted by IBM some years ago. And you end up with things like E and cosine and sine to ensure that you maintain the unit vector property and the unitary property, right? But just know there's like a pretty generic family of things you could do here. So this is what a quantum computer program usually looks like when it's presented to you. So you have your quantum score, you've got some qubit lines, and then we have some standardized gates. These are some of the popular ones, which are applied to certain qubits. We have like 1 qubit gates of certain families, H, T, T, dagger, complex conjugate, then complex conjugate transpose. Then you'll have like some multi-qubit gates, so you can generate entanglement, like this one here. I'll talk a bit about these shortly, but that's what you'll usually see when people talk about a quantum program. One of the important tasks that you have to do in quantum computing is transpiling or compiling, because in practice, you may want to implement a particular unitary gate over 2 or 3 qubits, but the computer will only support a subset of all the gate operations you want to do. So you'll take the generic unitary that you want, and you'll find a way of decomposing it into a bunch of smaller gates. And that leads me naturally to the next section where I talk about quantum gate sets and why they're important. But I'll just pause. Questions about unitary matrices and operations on these quantum vectors? Okay? It's easy, right? Okay. Let's talk about some common gates and how they operate. So, real quantum computers are only going to support a subset of all the possible unitary operations. And so it's important to think about, like, well, what are the standard subsets of operations that are supported, and which of them are going to be sufficiently general that you can do something like useful, like all of quantum computation. The first important set of gates to know is called the poly gates, or the poly matrices. They are given the names I, X, Y, and Z. And they're all represented by these 2 by 2 matrices. So you'll see them written like this. Just keep in mind, like, those are all could be more general complex numbers. But here we just have conveniently coefficients of like 1 or -1 on the entries for real and imaginary parts. Each one of these gates has kind of an interpretation. I'll just do one of them, which is the X gate. The X gate essentially swaps the entries of the quantum state, and it's sometimes called the quantum generalization of the classical NOT gate. So this will often be called like NOT, or the NOT gate. So that's the matrix it has. Let me show you why people call it the NOT gate. Imagine that we're starting our quantum system in the 0 basis vector, and then we apply the X gate. What does that mean? We have our vector of 2 complex numbers where all of the mass of the unit vector is in the first entry. That's the 0 entry, right? And none is here. Now we apply the X gate, we apply this matrix, and now it changes this state to this state where all of the probability is in the bottom. So that means that we have 100% probability of seeing the 1 vector when we read the quantum state, right? So if you just look at it, it's like we went from a 0, we applied X, and we got a 1. That's exactly what classical NOT does in logic. So that's why people say it. It also works in the other direction. That's important, right? If we start with 1 and we do this math, we get 0. So that's the X gate. Next question is, with these gates, how do we generate superposition? Because this does not produce a superposition, right? It's all in 1 or all in 0. How do we produce a superposition? The Hadamard gate is one of the convenient tools for that. It has this form. You have that multiplier of square root of 2 to keep the matrix as a unitary. And here's an example of what the Hadamard does. So if we have 0, so 100% of the probability in the 0 state, we apply Hadamard gate. Then we end up having 1 over square root of 2, square root of 0.5. That's how I've been writing it up until now. In the 0 state, and 1 over square root of 2 in the 1 state. This is also like written this way. So you can, like, if you think of this as the basis vector 1, 0, and this one is the basis, or this is the quantum state 1, 0, this is the quantum state 0, 1. Now you multiply them by square root of 2, you can see it adds up to this vector. So sometimes you'll see it written like this. If it's 1, it does the same thing, but now there's a negative sign in the lower part here. So it would be like, the probability of measuring 0 and 1 is the same, but like actually the quantum state is slightly different. You'll often see in quantum programs that you start from the 0 state. That's the default initialization for most quantum computers. And then many algorithms will start with a bunch of Hadamard gates on every qubit. Why is that? If you apply Hadamard gates all together like this, you end up in the uniform superposition state over all bit vectors. So I won't go through that now, but I leave this as an exercise you can try to understand, like why doing Hadamard independently on all the gates puts you in a uniform superposition. What about entanglement, right? So to do entanglement, we're going to need a 2-qubit gate, right? We need 2 qubits to have an entangled system, so we need a 2-qubit gate to build it. So we need a 4x4 complex matrix to generate entanglement. The most popular one is called controlled knot. Why is it called controlled knot? It's also called CX, for C for control and X for the quantum knot gate, which I introduced before. It's written like this, so a line that crosses 2 qubits with a little circle and a big circle and a little circle. It has this particular structure. But what does it do? If the control gate, or the control qubit, which is the small black dot, is in the 0 state, this gate will apply an identity matrix to the target gate. If the first qubit is a 1, it will apply an X gate, so swap the state of the second qubit. So now you can kind of imagine why it's called controlled knot. If you look at it just on the basis vectors, it has the effect of knotting the second qubit, but only if the first one is 1. So you start with 0, 0 is not interesting, nothing happens. If it's 0, if the first qubit's 0, then it applies the identity gate. So 1 becomes 1. If the first one is 1, it flips the second qubit. So if this one goes from 0 to 1, and this one goes from 1 to 0. So that's how you build entanglement. So if this is what we need to build entanglement, let's try to build a quantum circuit that will prepare the Bell pair state, the maximal entangled state. So I told you before that this particular quantum state, where you have all like 50% probability of seeing 0, 0 and 50% probability of seeing 1, 1, is the maximally entangled state. I will declare, without giving you any intuition, that this quantum circuit prepares that quantum state. So we start with everything in 0, 0, Hadamard, and then C naught. Without building an intuition for how to do this, that takes, I think, years of playing around with quantum programs. But you can convince yourself it's right or not just by doing the algebra. So here I'm going to color each part of this program and then show you how it turns into matrix operations. So first thing to remember is that if we're going to write this as matrix algebra, we have to reverse the order. So we start with 0, 0 on the right. We apply a Hadamard on qubit 1. So I'm using the subscript 1 to indicate which qubit that operation is running on. And then I apply C naught between qubit 1 and qubit 2. If I write this as matrices, this is what it looks like, okay? So basis vector starts up here. So we have the basis 0, 0, 0, 1, 1, 0, 1, 1. And because the quantum computer starts in the 0, 0 state, 100% of the unit vector's mass is on 0, 0. These colors kind of indicate where it comes from. So like blue is why we get the 1 here. Hadamard is why we get all these square root of 2's here. And then the C naught is that matrix there. Now, I'll just ask you to believe me that if you multiply all these together, you get exactly this. I think you can kind of see it, like how it happened. But trust me, it is true. The thing that for me is the most counterintuitive about this is actually the Kronecker product. So why does the Hadamard gate, which looks like this, turn into this big matrix? Because when you take the Hadamard gate and your Kronecker product with identity, it expands it out in this structure. So that's, to me, that's the most counterintuitive thing about all of it. And that's why it's really important to understand when you see a quantum circuit like this, there's actually like an implicit identity right there. So that's the end of the gate section. Next is on challenges and uses of quantum computers. Questions? Yes? Yeah. It's not all, but a fair number. You'll see it.
Yeah. Why this is the case?
Oh man, that's a deep one. I'm not sure I even know the answer. I'm not a quantum algorithm designer, okay?
Actually, this happens in feature mark phase, probably. So why this is the case, I don't know.
So I think my best answer to your question, which is why do many algorithms use this uniform superposition state, is that if you're like looking for a needle in a haystack, right? You might as well start with a small probability on every needle, every piece of hay in the stack, right? And then through your algorithm, try to amplify the probability on the one that you're interested in. So maybe that's the best intuition I can give you.
Like in line with the purpose that we started vacuum state, right? So yeah.
Yeah. Other questions? Yeah. Oh, that's a physics thing. So the question was, why are we only limited to unitary operators? I don't know, other than the physics seems to say so. It does. From what my understanding is that if you make even small generalizations to this model, all of a sudden absurd things happen. Like quantum computers can solve NP-hard problems, and it becomes way too powerful a model of computation. So it seems like there's a pretty fundamental reasons why it has this limitations. That said, there is a technique, which I won't cover, called block encoding, where essentially you increase the dimension of the space that you have, and you put your data in a sub-block of the whole system, and that allows you to do non-unitary operations on your matrix. So by increasing your space, you can get more general model, and many quantum algorithms use that because it's like unitary is too restrictive. So there are tools, but they are not covered. All right. Let's just very briefly talk about challenges and uses of quantum computers. So, I hope it's clear now that it's a pretty restrictive model. It's kind of hard to use. So what useful computations can you do with these unitary transforms over large matrices? There are really only a few great answers right now. So you have things like simulating quantum systems, which is essentially solving the Schrodinger equation is one good example. Factoring integers, which is Shor's algorithm that would, impact RSA encryption. That's one of the reasons quantum computing has been invested in for so long. There's a unstructured search algorithm called Grover algorithm, linear system solvers with HHL, and recently some nice work on simulating large collections of oscillating springs. So these are some of the examples where we know there's like a good quantum algorithm and we don't think there's a good classical algorithm. Maybe there's more, but it's very slow to, quantum algorithms are kind of very slow to be developed. So there's only a handful of them right now. I didn't go into, showing you any real quantum algorithms, but I can refer you to this paper, Quantum Algorithm Implementation for Beginners. It's a LANL technical report. And basically we go through a pile of these kind of well-established algorithms and show them running with gates on a real quantum computer for small numbers of qubits, like 5 to 10 qubits. So you can see what the algorithms look like. I hope it's also clear that quantum computing is not magic. Contrary to what you may hear in the news, it's actually kind of rare that a quantum speedup exists for any given application. There's a very nice kind of Scientific American article by Scott Aronson, who's a computational theorist, where he talks about the limits of quantum computation and why you shouldn't expect it to just solve like all our problems faster. So why should you use a quantum computer? A very active area of research right now is like developing strong arguments why a specific application would need a quantum computer or would benefit from a quantum computer. That's like a really good research activity to make those cases or counter cases. One good argument for why you need a quantum computer is that you have quantum data. So that's like why physics simulation is a great application, because the input data is quantum, the physics is quantum. It's a natural fit for a quantum computer. In many of the applications we run into, you just have purely classical data or classical optimization problems. Consequently, making a case that you need a quantum computer for that is pretty difficult. But it can be made, but it's definitely not as easy. We're on to part 2, state of quantum computing hardware. This is, everything else I have to say is much less mathy, less technically sophisticated. Any questions on the math part before I move on? Okay, let's talk about hardware, right? That was all just mathematical model of quantum computation, but we have real quantum computers. At the broadest level, there are 3 types of quantum computers that are kind of available or in the works. At the lowest level, we have analog quantum computers, and this is kind of like bare metal of the system. You're programming a quantum mechanical physics device kind of directly. One layer above that, we have the NISQ quantum computers. I mentioned that term before, and this includes one layer of abstraction, the quantum gates that we just talked all about. One of the challenges with NISQ computers is that the quantum gates are not perfect, so you don't have the exact model of computation I described before. A third level of quantum computation is called fault-tolerant quantum computing. And in this model, you connect a bunch of physical qubits together to implement an error correction code, which then implements a quantum gate model. So in that model, a fault-tolerant quantum computer, you can presume that all of your gates are implemented perfectly, but because there's 2 abstraction layers, it's going to be a lot slower, a lot more resource intensive than any other type of quantum computer. I'm going to briefly go through each type of these computers and tell you the case for and against. So what does an analog quantum computer do? You're directly controlling a quantum system, and it's going to be an open quantum system. Essentially, that computer is solving this ODE. So this is the Schrodinger equation. This is like a quantum generalization of a simple ODE, and it's just going to evolve it over time. You can use, like the natural use cases for this type of quantum computer are simulation of quantum systems, and potentially optimization. You might have heard of the company D-Wave. They build an analog quantum computer for classical optimization. It only implements one algorithm called quantum annealing. And so they've made a case that this computer could be good for that. The arguments for this technology is that it makes an extremely efficient use of quantum hardware, and it's very fast because it has none of those abstraction layers. The arguments against is that it's highly specialized to specific applications. Essentially, the hardware will implement some specific Hamiltonian here, and your application has to match that Hamiltonian very closely. The noise in this hardware, there's no quantum error correction for analog computers, so noise can impact what you can do with it as well. We have NIST gate-based quantum computation is the next level, and this is probably what you're most familiar with. You see it, here's an example of a gate program in the Qiskit modeling layer that's developed by IBM. It's exactly the model that I mentioned to you before, but with noise added on. So in this model, you get to apply imperfect gates to implement a noisy but potentially universal quantum computation. When I say universal, I just mean you can implement any quantum computation could potentially be in scope of these computers. And the natural use cases for these systems are doing quantum simulation of closed systems, variational quantum algorithms where you have to loop, like you loop a classical problem with a quantum computer inside. And then arguably quantum machine learning. This seems like the only system which is fast enough to basically train a quantum machine learning model. So that's an interesting point as well. So the argument for this technology and why many companies have sought it is that it's very flexible, right? In theory, all types of quantum computations are in scope of this computer. With the analog computer, it's like you can't do everything with an analog computer. It's also relatively fast because there's only one abstraction layer that needs to be implemented. That's the gates abstraction layer. The arguments against this technology are that noise can be limiting to the performance of the devices. And it's also unclear how you can, there's kind of a fundamental limit on how big the quantum program can be, which is set by the coherence time of the underlying qubits. So they have a fixed lifetime, and you just can't go beyond it. Given all of those limitations, some folks are interested in fault-tolerant quantum computing. So here, we're going to apply error-corrected quantum gates to implement universal quantum computation. And it will usually have a fairly restrictive gate set. So one example is this Clifford plus T gate set, which I'm showing on the right here. So it'll be even more restrictive than in the NIST computers. And the natural use case for these types of computations are quantum simulation up to very high accuracies, like higher accuracies than you could ever get with the noisy computers. We talked about factoring. We talked about solving linear systems. Those algorithms really require this type of computing technology. There's also been some proposals for solving nonlinear systems of equations with these computers. So there could be some very interesting applications. The arguments for this technology is that it's very reliable. You have error-corrected quantum operations. You have algorithms with proofs of correctness. The quantum error correction enables you to go beyond the lifetime of the qubits. So you add more qubits to your system, you can run longer quantum programs. That's not necessarily the case for other technologies. What are the arguments against? This requires a lot of physical qubits. The study, which I'm showing on the right, suggests that you need at least 100,000, maybe even 1 million physical qubits to get to an error-corrected quantum computer. I mentioned at the beginning of the talk, we're at about 1,000 right now. So we need a factor of 100 increase in the computer size to do this. So arguments against are lots of qubits. The algorithms require lots of quantum gates, like 1 million quantum gates, so you have to go really deep. And consequently, these computers are going to be much slower than all the other quantum computers we have today because they have all these abstraction layers and you need to do a lot of operations. So there's basically pros and cons for every one of these computing models. Let's talk about who is doing what in this quantum space. So we have our 3 types of commercial quantum computers. Today, you have some companies which kind of specialize in analog quantum computing. I'll mention Pascal is based in France, so that's a European-based company. We have other companies which are focusing more on noisy gate-based quantum computing. Those are ones that probably you've heard more of. But available soon, are meant to be fault-tolerant quantum computings. And there's a bunch of companies that are working in this direction. And the 4 on the bottom I mentioned have released public roadmaps where they say they're going to build their first fault-tolerant quantum computers, usually with around 100 logical qubits, sometime between 2026 and 2030. So it could be as close as 2 years from now, we'll have fault-tolerant quantum computers where you could try to run some of the algorithms that we were talking about earlier in the talk. So that's been a big and exciting point. Why are there so many companies all at the same time? The short answer is that there is no transistor yet for quantum computing. If you think back to the early days of classical computing, we had vacuum tubes, we had mechanical computers, we had all sorts of weird computing technologies, but it was the invention of the transistor that basically transformed everything into one dominant solution. Right now, there's no transistor for quantum computing, so like everyone has a different approach and a different qubit technology with different pros and cons. I showed this picture in the beginning. Now I'll add a little bit more to the information. So you can see there's different boxes with one says superconducting, one says quantum dot, one says optical, trapped ion. Each one of those boxes is a different computing technology. And you can see there's multiple players in each space. Every single one of them has like a pitch for why their qubit is going to be the best qubit. So there's a lot of interesting things happening there. Here's some information about different hardware platforms that I have used and kind of what the trade-offs they have in this NISQ era. Right? I've only used NISQ computers because those are the only ones that are available right now. But so for the superconducting qubits, they're kind of very fast in speed. They have medium levels of noise, but they're very scalable. So they've been demonstrated with like 500 to 5,000 superconducting qubits. Usually they're connected in a sparse topology, so you can only do a CNOT between certain pairs of qubits. The atomic systems, either trapped ions or neutral atoms, have a different approach where they're slower, they have a lower noise, and then they have maybe less scalability demonstrated so far. There's an interesting trade-off between trapped ion and neutral atoms, where trapped ions tend to have all-to-all connectivity in between the qubits, and where you can do a CNOT gate. The neutral atoms have different types of maybe sparser connectivity, but they have more atoms. So essentially, there is no clear winner here. Everyone has their pros and cons. Consequently, at least for now, you really have to think carefully about the hardware platform you're using and the application you want to run. Different hardware platforms are going to be better for different applications. So you really want to co-design your use case with a particular platform. So who will win the quantum computing race? The short answer is I have no idea. I mentioned it before. Everyone has a great pitch for why their approach is best. In a couple hours of talking to a vendor, I've never been able to figure out why their technology is better or worse than another person's technology. I think you just need a lot more time to understand all of the design trade-offs they're making. But I will say the following, which is that Gartner has a kind of an idea for how technology gets adopted, where there's a technology trigger, then there's kind of overinflated expectations, then everyone gets disappointed because the results aren't as good as they expected. And only after the trough of disillusionment does the plateau of productivity happen. And my experience is that things are kind of laying out in this way, where noisy analog quantum computing has been around a long time, and we're starting to see really interesting applications of that technology in the narrow set of applications where it applies, but it really is useful today. Noisy gate-based is somewhere in between the peak of inflated expectation or maybe the trough of disillusionment. I hear folks, kind of getting discouraged by those platforms because their results haven't been working, but it's hard to say exactly where it is. But a lot of the excitement in the last year has been around fault-tolerant gate-based quantum computing, because 12 months ago, folks would say, okay, that's 10 or 15 years away, which is kind of like positive infinity. People can just keep saying that every 5 years and no one notices. But now we have these public roadmaps where companies are saying, nope, we're going to have it by 2026 to 2030. So that makes fault-tolerant quantum computing a much more real potential, and now is a good time to learn about it. So I'm glad I could come and give this talk. So that's kind of the state of affairs. I think we do have time to go into the quantum computing for power systems part. But let me first pause. Does anyone have questions about the hardware roadmap or the hardware overview I just gave? Yeah.
Is that abstract layer happening in hardware level? Because as a user, if I want to implement my algorithm on a fault-tolerant hardware, does it any change between this and noisy hardware?
Yeah, so the question is it going to change when you go from noisy hardware to fault-tolerant hardware, your interaction with the computer? I don't think so, although I don't know because no one has a fault-tolerant quantum computer to show me the software stack yet. But I suspect like if you have a Qiskit program, which is IBM's modeling layer for quantum circuits, you would be able to turn it into a fault-tolerant program with very little effort. Whether the hardware vendors will let you access the lower levels of the stack, like maybe I have a fault-tolerant quantum computer. Can I use it as a NISQ computer with 1 million qubits? Can I run it as an analog computer where I just control all the qubits directly? I think that's a lot less clear. Like it really will depend on specific design choices the hardware vendors make. It does seem, I showed this picture before. So like there are some companies, like let's say QEra for an example, who are pursuing analog quantum computing simultaneously with fault-tolerant quantum computing. So maybe that computer, you'll be able to do both on the same device. And that could be fun and interesting. But I think it really depends vendor by vendor. I should also plug this company, Alice and Bob, over here. They're going straight for fault-tolerant quantum computing, and they're also based in France, which is pretty exciting. Other questions about the hardware? Okay, power systems. Last 15 minutes. Okay, so what can we do with this? Where are the grid science applications for quantum computing? So the first important thing to know is there's already a lot of papers about this, right? Here's a wonderful survey about quantum computing for smart grid applications where the number of papers they found blew my mind away when I read this survey. Like here's a bunch of different references where they are, showing different power applications, PMU placement, power flow, unit commitment, so on and so forth. And then like which papers studied them. If I recall correctly, category 1 is they just studied it in theory, and category 2 is they also ran it on a real quantum computer. This is an extended list where they really showed every paper and what do they show here? Like exactly the reference, the type of computation they were doing, what is the classical time complexity, what quantum algorithm they use, what is the quantum time complexity, did they run on hardware, yes or no, which hardware did they run on. It's really incredible. I can highly recommend this survey, which is now 2 years old. What I'm going to talk about is, so many people are trying these things. What I want to talk about is maybe a little bit more of the details of doing this kind of research, which can be important to look into. So in the survey, they identified a couple of examples where they were looking at power flow. So we are talking about simpler things than what I talked about in my first talk. So we're just solving a system of linear equations or solving a system of nonlinear equations. DC power flow, fast decoupled load flow are both linear equations, or AC power flow would be one system of nonlinear equations. Now, if you look at this table, it says that the classical computing time is around linear, O of n, where n would be the number of buses in the system. And the quantum version is log n. So that is a dramatic improvement over a linear speedup, right? Some people would call it an exponential speedup because you went from like linear to log. So at first glance, this looks super promising for doing quantum power flow, which is called in literature. But once you get into the details of exactly what it would take to do this, the story becomes like a lot more complicated. So recently we had a postdoc in our group called Parikshit, who, thanks to Spiros's panel last year at PES, was inspired to get into this field and study quantum computing for power systems. And so he's been working on this quantum power flow question for the last year. And in this particular paper, we do a deep dive comparing if you do a power flow solve, let's just do linear power flow solves, so it's like DC power flow, with a conjugate gradient method, that would be classical state of the art, to a quantum method, HHL, like what would the time be? So I'll just take you through the highlights of this paper. So the first challenge you run into is the solver complexity. What you will often hear people say is that quantum linear solvers are logarithmic in time. That is true in part. So what I'm showing on the right is the algorithm complexity for different, so conjugate gradient, the classical method, and HHL, the quantum method. N is the number of buses in the network. S is the sparsity of the Y matrix. K is the condition number of that matrix. And E is going to be the accuracy you want to solve the problem. What you see here is that conjugate gradient has sparsity, so S, which is the sparsity, times N, the number of buses. That's kind of like the dominant factor. And then you have some other factors here, like condition number and accuracy. Indeed, the quantum algorithm is logarithmic in N. So it's logarithmic in the number of buses you have in the system. However, it has a quadratic dependency on sparsity and a quadratic dependency on condition number. So these details are important, right? Like what happens with all these other parameters. I think in many quantum algorithm papers, when you read them, they'll say, oh yeah, there's a way to make the condition number constant or small or whatever. I don't think that's in general true. So like, you should trust no one. You should read the quantum papers in detail and understand everything about them. You should understand your application use case in detail as well. So it may be the case that HHL scales better when like this trade-off between N and condition number and the other parameters all are true. So it really depends on your application. So we asked the question, what does this really mean for power flow applications? So the goal is to look at power network data sets, understand their properties, and then plug them into these formula and figure out, like, is the trade-off actually favorable or not? First important note is that, and I didn't even know this till we did this study, but the condition number of AC power network data sets, at least for the PGLib ones that we currently have, it grows really fast with the size of the problem. So that's the picture you're seeing on the x-axis here. So this is the number of buses in your power network, and that's the condition number of the Y matrix, K. And this is a log scale. So you can see that like it starts out pretty small, like 10, and then it grows to like 1 million or 10 million. So really big numbers up here. In fact, what is the dashed line here? You're fitting a power law function to the size of the buses to the condition number. So we can get condition number as a function of network size. It's actually growing at a scale of like 0.18. So almost quadratically with the size of the system. So the condition number is growing faster than N. And you can already see that this is going to be a problem. Like in these two algorithms, this one is good in N, but worse in condition number. This one's better in N, or worse in N, but better in condition number. Because condition number grows like this, you actually want an algorithm that has the best performance on condition number, which is not the quantum one in this case. So complexity of the algorithm, that's like challenge number one. There's another challenge to using a quantum computer. And you can now appreciate this, that we did the tutorial. There are significant overheads to load data into a quantum computer and get the data out. So if you want to solve a system like AX equals B, on a classical computer, you can just solve it directly and read. On a quantum computer, first you have to prepare all the data as a quantum state. That's this right here. Then you get to apply your quantum algorithm, and then you have to read the data out to get your classical data X. So what does that mean in terms of quantum? We start with the initial state 0. We apply some unitary. We load all the data. We have now psi1. Then we apply our quantum solver algorithm. That gives us psi2. And then we read the data. First thing, like, there's no way to load this data without paying linear time, right? You need to write every entry in your A matrix. So this part of the algorithm has to take at least linear time, not log n time. So when you read a quantum paper, they'll often just talk about this critical subcomponent of the algorithm. But you need to also consider, like, what is the time to load the data into the computer? So that's one challenge. What is the complexity of reading out this data from the quantum computer? That's another important point. You need to know how you represent the solution in the quantum computer. So we have our psi state at the end. In most linear system algorithms in a quantum computer, they use an amplitude encoding of x. So what does that mean? The amplitude of the quantum state, each entry, is going to represent the value, the continuous value x. So like here, the solution would be like 0.2, 0.1, 0.4, 0.3. That would be the phase angles of the DC power flow problem. But remember from the tutorial, when you read a quantum state, you don't get to see this complex vector. If you did, it would be amazing. Instead, you have some probability distribution over basis states, and then you just get to read a 1 or a 0, right? Do you see the problem? So if my solution to my power flow problem is the probabilities of seeing all these basis states, to get these values, I need to read the quantum computer thousands or millions of times to be able to reproduce what these coefficients are. So now we have a factor of, let's say, 1,000 or 10,000 in front of our whole quantum algorithm just to extract the data out of the quantum computer. So yeah, measuring this is really tricky. So the key result in this paper is the following. We look at end-to-end complexity for running HHL on a quantum computer, which includes the data loading. It includes the readout complexity. We take the parameters for, based on the pglib dataset, we can write the condition number as a function of the system size. And then you end up with a plot like this, where the scaling of classical algorithms actually looks much better. It's like n to the 2.5 than the quantum algorithms, which is like n to the 4. So unless we have a new quantum algorithm that lets us change the complexity quite dramatically, it looks like for this particular application, quantum computers will just be slower than classical computers once you incorporate all of the overheads you need. So what is interesting research I think that's worth doing in power systems right now with quantum computers? The first thing I would say is designing application requirements for quantum computers is extremely valuable. So this is sometimes called quantum resource estimation. You can think of it like, for a given application, power flow or whatever, the quantum computer must run this fast and must be supporting data sets of this size to have an impact. You can use these types of research to either make an argument like this looks like it will not work, like you could never build a quantum computer that has these properties, or like the forecast when the quantum computer will come that can do this. So you could imagine looking at a roadmap and saying, well, we need it to be this fast and this big. That'll happen in 2030 or that'll happen in 2050. This paper by Microsoft is a great reference for what it's like to do that assessment. And then the second one is application benchmarking on a quantum computer. So I mentioned at the beginning of the talk, we're in the NISQ era now, and there's no proof quantum computers are better. They might be better. The only way to really know is to try your application on a real quantum computer and see what happens and understand the strengths and weaknesses. So the characteristics of these NIST devices are not well understood, especially in applications. So just benchmarking your favorite application is a very productive thing to do. And to highlight a paper doing that in power systems, it's my pleasure to highlight this one from this group. I think it's going to PSCC this year. But they looked at hybrid quantum classical algorithms for mixed integer optimization. So you're going to take a mixed integer program like transmission switching on the power grid, and you're going to do part of it on your classical computer, make a subproblem that you can send to your quantum computer, and have those two interact. What they showed in this paper, like, so here's kind of the key table of results. Here's kind of the standard classical methods. Here's where the quantum methods are. They showed the algorithm worked. It found high quality solutions. There's an argument that it converges in more, like less iterations. So in iteration count, it's faster. I think this is a great example of some very important methodological work you could do on a quantum computer today and get us ready for future quantum computers. Now, one thing that this paper doesn't do is it doesn't show that it's dramatically faster than a classical solver. You can see the runtimes are right here. I think that's okay. And this is something that I work like to communicate with people, that like it's too much to ask your quantum computer to be faster than all the classical computers right now. But if good methods may be extremely valuable in the future. So if I'm reviewing your paper, it doesn't need to beat all the classical methods. You just have to have a really good idea for how you're going to use a quantum computer. And I think that should be the bar that we set when we're reviewing papers for the near term. So I'm at time, so I'm going to skip the optimization part. It's a lot, but it's my favorite. And I'll just wrap up. So, okay. Quantum computers are fascinating. I hope I've convinced you of that. And hardware is very limited right now, but it's improving fast, so it's a good time to learn. Identifying promising applications is really difficult, but it's super valuable. So go for it, please. There are some promising results in quantum accelerated optimization. I highlighted the paper from this DTU team doing that, so I think that is a promising direction, at least in the near term. And developing these really strong cases for quantum applications in power systems specifically, I think is pretty open. So great research topic for the future. So with that, I'll conclude. Spiros, is it okay if I take a couple questions, or do we want to wrap?
Yes, I think that's absolutely fine.
Okay, we got one there. Can we expect quantum hardware to get faster?
No, I mean, instead of, in addition to speeding up thing, can we expect more from quantum hardware? More specifically, I'm talking about power flow and optimal power flow. Do you think that there is more opportunities in exploring like this kind of algorithms?
Definitely exploring new algorithms is a great idea. I mean, I think the problem we have is that the algorithms we know have tons of limitations. So if you can get rid of one of those limitations, it may change the whole story. But I would say it's tough to develop new quantum algorithms usually. But yeah, I think it's a good research direction.
Different aspects of programming and computation with quantum hardware, because here we see that we cannot that much count on this like speeding up, but maybe there are more opportunities in exploring quantum hardware, right?
Yeah, absolutely. What I hope to communicate with this is that you should not blindly apply like algorithm complexity and just say like it's going to be great. You should understand the whole details of your application and document why it has potential. I think maybe what you're getting at is if we broaden the scope of the question to not just solve one DC power flow, but to look for distributedly robust DC power flow, or like just change the problem, maybe there's a new opportunity for quantum there. And absolutely, like making the problems harder is probably a good idea, because then it'll become difficult for classical computers, and maybe there's a narrow path the quantum computer can go fast. I think we got one up there.
Yeah, you kind of already touched on that on my question. I wanted to ask what your what your view is on the potential for applications like stochastic optimization or like near optimal solutions, because I think this is very naturally you can implement a lot of like probabilities in your input process in the qubits and also in the output where you read from the distribution and not like a deterministic solution. So what is your view on that? I guess there's a lot of potential in that regard.
Yeah, I would agree with you. There's a lot of potential because, like as you've seen, right? Because quantum computers have a probabilistic nature, then studying stochastic problems is kind of a good fit. What I focused on in this talk was really deterministic quantum computing. So it's like we want to find one optimal solution, or we want to find one solution to power flow, right? And maybe there's enough evidence now to say that's too easy a problem for these computers, and we need to broaden our scope to sampling from difficult distributions in power systems. Or another point you mentioned was not seeking optimal solutions, but seeking close to optimal solutions. Absolutely, I think if your goal is to find the optimal solutions to problems, quantum computers have a very difficult case. Because I showed in the complexity picture, they don't solve NP-hard problems. So you're asking it to do too much. The quantum algorithm should also be an exponentially long running compared as well as the classical. So approximate solutions are much more likely to be good on a quantum computer than exact optimal solutions.
Okay, maybe one follow-up question. Can you expect that when you have your output distribution, so like you said, you have to kind of sample from this output distribution, can you expect that your kind of near optimal solutions will be also having high probabilities in your final quantum state? Or is that like you need to program that in a specific way?
It depends on the algorithm, and that's a research topic. In my experience, the two dominant algorithms for quantum optimization, combinatorial optimization, are QAOA and quantum annealing. They seem to have a property that as you approach high quality solutions, you kind of get a distribution of high quality solutions near like a pretty even distribution. So then they become very good tools for sampling very different solutions that are all high quality.
Okay, we'll take one last question and then because it's time for lunch, right?
Thank you. I was wondering, perhaps not the biggest selling point of quantum computation is perhaps the speed up, but also like in terms of complexity when I have to aggregate a network because it doesn't fit on my hardware with a conventional computer. Perhaps we should also focus on this when we try to advertise quantum computation in power systems that, well, I mean, I'm not fully convinced that perhaps we can be faster than conventional computers, but I really like the possibility of having such a more complex system to be able to compute with the exponential factorization of qubits over conventional bits.
Mm-hmm.
Could you touch on that? Like, do you think perhaps complexity is more of a selling point?
So what I heard you say was, could one of the dimensions be the advantage of the exponential space over just speed? And I think that intuition is a good one, right? So can we, that's one of the key advantages of quantum computers. So like if we can exploit it, we should. The thing that's not super clear is you said that the data doesn't fit in the memory of your classical computer. So how are we going to load it into the quantum computer? Would we have multiple classical computers, like feeding instructions to one quantum computer? That could work. It's important to answer that question. The way that it works in quantum physics is that the data has a tensor structure. So the Kronecker product allows you to make a huge dense matrix with a very small number of quantum gate operations. So if your data has that form, you can basically load it in constant time and then start processing an exponentially large matrix. But it's showing your data has that form is an important challenge to address in a research topic.
Great. Thank you very much, Carleton. Let's give